Here, start here. Then. Yeah. We're getting there. We're close. All right. Let's do it. We'll clap to start our audio. So yeah, here to just answer questions. You got homework questions? Just give them to me. You can just do questions until then. All right. Let's make sure our Nightbot is in the channel. Pull up our chat and we will get started. Beautiful. Okay. Cool. Let's do it. So when 5 is not x, when x is not 5 and x is not -5, this whole thing is equivalent to. Okay, so they want us to bring it together. So it looks like we can probably factor these things here. So let's do that. X squared minus 25 is the difference of squares, 2 squares. So that means x plus 5 and x minus 5. And that's pretty close to this. In fact, anything that is a minus b, you can sort of like say it's the same as b minus a as long as you put a negative sign up front. So in fact, they are the negative of each other, right? Okay, so then we're safe saying 5 minus x. And then we can just put a negative sign up front and we can deal with the consequences. So let's say here, this becomes x plus 5. I'm gonna put the negative back, but it's the same thing. I'm going to say -1. It's the same thing as putting a negative. It's a -1. Okay. Okay, so that's the whole left side. And that's 2x. This one we're going to keep this way. Maybe a silly way to do it. Maybe we should have switched this one, right? Because we could have turned this into x minus 5 as long as we put a negative sign up front. Okay, but who cares? We did it wrong, so let's just do it. I don't want to pull that up. Okay, so what do we got here? So let's find a common denominator, right? It looks like this needs a -1 and an x plus 5. Okay, so it looks like we're going to add a -1 to both sides anyway, so let's actually do it that way. Now that we've caught it, instead of switching the one on the left over here, we're going to switch the one on the right. Right? And so this is x minus 5 still, and the negative shows up here. So then we just have to add an x plus 5 up here. This is already taking too long because of that whole process, but that's okay. Who cares? So what we did was added an x plus 5 on the top and the bottom. And that denominator stayed the same. And now this is just a negative sign, so I can actually bring the negative sign up top if I want to, or even out front, and just say minus this whole thing. Okay? So let's do it. So 2x minus x plus 5 2x is what's on top. And on the bottom, we just have that x plus 5 x minus 5, right? Which the whole time was actually this anyway. So if you'll notice, the denominator is all the same, right? So we don't really need to go further with the denominator. Let's just take that numerator, and we're looking for this. So let's distribute the 2x to both these things, right? So this becomes minus 2x times x plus 2x times 5. So see how that is still x plus 5, but each of them has a 2x. Okay, so now we can distribute the negative. We do the same thing with the negative. Right? Okay. Let's keep it going. So what do we get? 2x minus, and this is actually 2x squared, and then minus 10x. So these two can come together, and we have a minus 2x squared, and so it looks like we're looking at b here. Okay? Right? And the whole thing was this denominator the whole time. So that's B. Okay, let's keep it going. I think I can do this. It's not a bad way to do it. Deal, but Schwex. Okay, unless somebody jumps in here, let's just keep doing the questions that I have. So these are questions that I've recently done with some students, and common kind of areas where they struggle. But look forward to hearing kind of what your questions are. If you need to, you can join the Discord and ask your questions there, or we can even get in the voice channel and you can join live. Okay? So yeah, just quickly, let me just take a drink here. Okay, groovy. that's the preview. You could see it the whole time. Okay. So solve the equation where x is between these two values. And the equation is this. Okay, so go down just a bit so I can do that. Okay. So what I should look for really is, I mean, this is a lot of signs, and I'm not really going to be able to bring together a sine squared with a sine all that easily. Okay? Just like I'm not going to be able to bring together an x squared and an x all that easily, right? Like, we have to sort of add complexity here to how you figure out, you know, what x is, because there's two x's and you need there to be just one so that you can isolate it and get it to be just an x equals statement, right? So if you have an x equals and the squared is over here, then you're not really telling me what x is, because it will change, right? So we need just an x on one side. Well, to do that, we're gonna have to see the same sort of quadratic nature. So I'm gonna do something here to change the way you see this. I'm going to make the sine of x equal to w. Okay? So sine squared will be w squared. You might see where this is going. This is I'm going to use the same substitution here. So the sine of x is w. I have to use the same substitution, really. I don't have to, but I should. And now this isn't too far off from something that we would have solved, you know, a year or two before this equation, right? There's still another complexity we have to be careful of. That's probably going to get most people, but we'll see it when we get there. Yeah. So, okay, let me just put this there a little better. Okay. So, yeah. Okay, so now we can solve this. Remember, the trick is get it equal to 0, because then once you get it looking like this, the only way a and b multiply to be 0 is if either a is 0 or if b is 0. And now this is an easier way that, you know, if this is x plus 7, this is x minus 1, this, you know, could result in a squared, oh, sorry, not x, but w. Right? Going backwards, this could result in a w squared, right? But now here, each of these is just going to be a w. So this is going to say like w plus 7 is equal to 0. That's what a equals to 0 means, right? And that's nice because that's easy to solve, right? So this solves the problem of getting this squared and not squared thing together to solve into just this thing, okay? And we'll do the same thing with b. Okay, so all that is mumbo jumbo. You don't need to know any of that to proceed, but that's kind of where we're going. So let's go back and let's solve here. And I'm just going to kind of quickly run through this. So I would simplify this to be this plus 1, and I added 1 to both sides. And now this is w plus 1. W plus 1, that is the factoring that we can do there. And so w must equal negative 1. In both cases, it's the only way that this is equal to 0. Yeah? So there's actually only one solution to this. Okay, but that's w. W was our story. So let's kind of like go back and let's say that w is equal to negative 1 is what we got as a solution, and w the whole time was the sine of x. And so the solution has to be to solve for x, and so we're looking for this in degrees. This is an angle that has a sine of that angle, right? Or a sine. Okay, I'm not even gonna do this. That's it. The language there is sort of sketchy if you're not comfortable with the landmines that are sine of plus negative, right? And sine of cosine and all that stuff. So let's just say that the x is equal to the sine inverse of -1. That's how we undo the sine, right? And what has a sine of -1? That means it's a height of -1. I think we're looking at 270. Right? So if you need to, you can ask your calculator this question, but you should get the same answer. Okay? So we did it. So, you know, this one we actually kind of got lucky. If this was, for example, 1/2, and we got to the point where we were solving for this equation, we would have to be careful that there are 2 solutions. Right? So let's just say, what if this, there are 2 solutions. Okay? So just look out for that possibility. Okay? We kind of got lucky that this is one of those times when sine is only one thing. Okay? And I think we solved everything because this was actually a perfect square. Okay, so this also could have been 2 solutions, and then we would have been left with 2 values of w, and then we each could have had 2 solutions, so there could have been 4 solutions to this. Okay? Okay. Anyway, let's try this one. This is actually pretty interesting. I haven't tried this one, actually. This is something that we got to at the end of a session together. And I thought it was pretty interesting. All right, I think I maybe saw this. I don't know actually where this came from. I think I saw this as the next question, something that we were doing. Regardless, okay. Using the set of data that follows, calculate how many of the molecules of oxygen that were used in aerobic catabolism by Julius Caesar are in each liter of atmospheric air today. All values given are expressed at standard conditions of temperature and pressure. See appendix, therefore can legitimately compared. So the average rate of CO2 consumption of a human being. So I'm kind of catching that right there. That's probably going to be valuable. So a human male during ordinary daily activities is 25 liters per hour, okay? So that's how much oxygen we consume in an hour. 25 liters of oxygen. It's actually quite a bit, because it's not, I mean, our lungs are like, your tidal volume is like a liter, and you breathe, let's say, every like 2 seconds, full exhale. Wow. So what, 30 liters a minute, and 180, no, yeah, 1,800 liters an hour, and 25 liters of that is oxygen. Wow. Okay, so this is how much we breathe. And this is how much of it is pure oxygen. And this is approximating. Okay, this is, you know, values just so I use in my head. Number of years after his birth when Caesar was mortally stabbed in the Roman Forum. Okay, so 58 years. So 56 years was Julius Caesar's life. Okay. Number of liters of O2 per mole. Okay, so 22.4 liters per mole of O2 per mole. Okay, sure. Number of moles of O2 in Earth's atmosphere. Okay, sure. Moles of O2 on Earth. Okay. Number of molecules per mole. Okay, so this is just our AV number. So this is Avogadro's number. Okay. Amount of O2 per liter of air at sea level is 195 milliliters per liter of O2 air. Be prepared to be surprised. Of course, criticize the calculations if you feel they deserve criticism. Okay. So, what are we asking here? Just go back. So, we're asked about Julius Caesar. And this is pure oxygen. Consumption. Human male consumption. Okay. Calculate how many of the molecules of oxygen that were used in aerobic catabolism by Julius Caesar are in each liter of atmospheric air today. Okay, so what we need to compare is 1 liter of air today versus molecules of O2 used by JC Julius Caesar, baby. All right. Okay. So in one, I think it's this way. How many molecules of oxygen were used by Julius Caesar per liter of air today? Okay. And we have all these values to sort of account for. Okay, so let's, that was my number. So let's use all these for here. Okay. So let's first find kind of like the number of molecules of oxygen that were used by Julius Caesar. Okay, so let's call this part A, and let's call that part B. Well, I mean, let's just say part A here. So what we're going to do is we're going to take 25 liters per hour, and we're going to turn that into, so that's of O2 per hour, and we're going to turn that into, or use the whole life to sort of say O2 per lifetime. of JC. Okay, so let's figure out how much oxygen was used by JC in liters, and then we'll have to convert that to molecules. Okay, so first we'll sort of do this in liters. About 2. Volume about 2. Divided by the time of JC. So the time of JC is JC's life in hours. So let's first maybe calculate that. So that is let's maybe just do this here. So that's how we convert this 56 years into, what do we want it in? Hours. Okay. So to do that conversion, we're going to multiply it by a bunch of versions of 1. Okay, the first one is in 1 year. There's 365 days. Obviously, I'm going in that direction. I'm getting days before hours, right? And the reason I set it up this way is because I have years up top here. I don't want years anymore, so I have to cancel it out. The only way I cancel it out is if it's on the bottom. So the question is, or sort of like, we're always going to use something that's equal to the top and the bottom, because otherwise they're not equal to each other, and then we're multiplying it by something other than 1. We don't want to change this number. We want to multiply it by a tricky 1, right? The tricky 1 is 1 year is the same as 365 days. And we can even add a 2.25, but it doesn't look like they care too much in this problem. And the other 1 we're going to use, now we have it in days, right? We don't want it in days. We want to get rid of days. So let's put days on the bottom here. And what do we want to turn it into? Hours. Does anyone know how many days are in an hour? How many hours are in a day? Well, 1 day is 24 hours, right? I could say how many days are in an hour. I could say 1/24th of a day is in an hour, right? But that would be ugly. So let's do it this way. And now we can cancel days, and we're left with hours, which is what we wanted it in. Okay. So now we will have 56 times 365 times 24 hours. Okay. So let's figure out what that is. It's 56 times 365 times 24. So that is 49.0560 hours. Yeah. Boom. All right. Okay, so that's how many hours Julius Caesar lived. And what glorious hours. What were we doing here? Okay, so now we needed that for this value here, right? And then the volume of O2, we want to sort of figure that out, right? And so we're going to have to sort of like do this conversion here, right? So this is the amount of volume per time, right? And so if 25 is to 1, the question is kind of what is the volume that is equivalent to 490,560, and it's just 25 times that value. Uh-oh. Okay. So this value is 1.23 times 10 to the 7. Ooh. Pretty big. Okay. So that is the volume of O2 in liters during JC's lifetime. That value there, right? So we need to convert that into, so let me just get organized here. That was our conversion into hours. So let's just a little smaller. And do this. Bring that down here. There. Boom. Sorted, sorted, sorted. All right, boom, sorted, sorted, sorted. Boom. Okay. Okay. So that's the volume of oxygen in liters during JC's lifetime, not the big JC, the little lowercase JC, Julius Caesar. Okay. So, but that's volume. So we don't want volume, right? This is 1.23 times 10 to the 7 liters. That's that volume of O2, right? Or let's just maybe say volume of JC, right? And the volume is O2. So let's do this. Okay. Or maybe we just do this. Right? Well, we want molecules, so we're gonna have to convert that using Avogadro's number, right? And this number here. So the number of moles that are in a liter. So let's use that. So the number of moles that are in the liter, that's kind of like our concentration, and number of moles that are in a volume, right? So this is 22.4. Oh, sorry. This is 1 mole. And this is 22.4 liters, right? And what is the volume that we have? So what I've just plugged in there is the concentration. They told us. And we're going to solve for n, I believe. So 1.23 times 10 to the 7 liters. And so we're going to solve for n. N is equal to, what is it? 23 times 10 to the 7 divided by uh-oh, don't do this to me. Come on now. Thank you. Uh, 549107 point. Oh, that's fine. That's the number of moles of O2 during Julius Caesar's lifetime. Yeah? Okay. So this is the number of moles, right? Okay, so let's kind of say that of the 3.7 times 10 to the 19 moles of O2 in the atmosphere. So that's kind of like our total. Of those, as long as we can kind of assume, and this is, you know, probably not a safe assumption, because assume that when you're sleeping you kind of, actually, maybe not actually. No, this is a pretty safe assumption, because you're going to consume these, okay? You're going to ingest them and consume them. Oh yeah, okay. I mean, this is fair. We can criticize this. So the last step is, of course, criticize calculations. So I just thought of a kind of criticism that you'd consume these oxygen molecules and turn them into CO2, and then that CO2 maybe goes into a tree, and then it's never seen again. So, okay. But let's just keep on keeping on here. So 549,107 moles of O2 that JC interacted with, let's say. Okay. And so, yeah, so this is kind of like of the, you know, how much JC is in this sort of like air today, right? That's what this ratio is going to be, because this is going to be moles over moles, moles of oxygen over moles of oxygen. They're going to cancel out, right? So this is going to be just like a fraction or percentage, right? So let's turn this into a percentage here. It's probably going to be pretty small because of how big that number on bottom is, but let's just deal with it when we get there. 549,107 divided by 3.7. Okay, so that is 1.48. This is the proportion. Okay, let's just add a 4 there because it's pretty nice. So this is the proportion, or if we move the decimal place 2, right? Remember, if you get this, that actually means 73%. So what you do, you move the decimal place twice, which is really just changing that number, right? So let's make it not as bad, and that is the percent, right? It's still like a, this is a billion, this is a trillionth of a percent. This is about 2 trillionths of a percent. Okay. 2 trillionths of a percent is are of the molecules in the air today were interacted with by Julius Caesar. Pretty interesting. Okay, wait a second here. Is that what they asked for? They said the amount of O2. Okay, wait, what did they ask for? How many molecules? Okay, so we're going to have to convert this to molecules, and this is actually going to be quite big then. Of O2 that we used are in each liter of atmospheric air today. Okay, so we're going to use a liter of air. Right now we have just of the oxygen molecules. So let's kind of use that to talk about air, right? So we're going to assume that only Julius Caesar has interacted with the oxygen molecules, and this is one. So 1 liter of air contains that many milliliters of oxygen. I'm just going to convert this to liters of oxygen, right? And now we can just really use this as a ratio to say, well, if you, let's say you only have 0.02% of the oxygen molecules, and I now add more molecules by making it air, right? I add 5 times the number of molecules. Well, now you're going to have even less, right? So another way we can think of this is to multiply really this this division here. So we're going to multiply by this here, and this is 1.484 times 10 to the negative 12 of the oxygens. Okay, and this is the O2s in the air, and so those cancel, right? And now we have, or we can even just say this. And so what do we multiply here? We multiply by 0.195, divide by 1, change it, we get 2.894 times 10 to the negative 13. Okay, and so that is percent of the air that's been interacted with by Julius Caesar. All right. Okay, I don't believe we're done yet because we still have to say molecules, right? This is just the moles of O2, right? Yeah. So this is the percent of the moles. Here. Have been interacted with by Julius Caesar, right? And so let's convert this to molecules. So 2.894 times 10 to the negative 13 divided by 6. Well, we're just using 6. Oh, wait, sorry. This is multiplied. 6 times 10 to the 23. Molecules per mole. This is moles, so the moles cancel. We are left with that times 6 times 10 to the 23. So we get 1.74 times 10 to the 7 molecules. Right? Should I take away percentage here? I think I should just keep this as a 14. Because that's the proportion, so that means this is a 15. This is a 15, and that means this is a 9. So what this says in sort of language is about 1.5. No, sorry, 15. No. Yeah, that's right. 1 point about 1.5 billion molecules of molecules of O2 from Julius Caesar are in every liter of air. Oh, you can't see this. What am I doing? What kind of streamer am I? None kind of streamer. I got one viewer. Thank you to the one viewer. Appreciate you. All right. Boom. Okay. So this is, let me just add the caveat here according to this question. Why does my writing look like a child? Okay. Oh, let's change this to more than 1.5 billion. More than 1.5 billion molecules of O2 from Julius Caesar. That Julius Caesar breathed. Let's say that. Or Julius. Boom. Okay, let's take a little break on that now. That's a little crazy revelation there, isn't it? It's a little crazy there for you. Oh God, me water bottle. Me water bottle. Fucking hell. Sorry about the language. Nobody listening anyway. That's okay. Beauty of it. Okay, let's bring this down here. There. Not there. Not there. Not there. Not there. That there. Okay, let's bring that there. Okay, let's put this over here. Okay. Let's move that. Let's bring that. Let's do that. We'll wiggle this. Stay with hold that. That over here. Do that there. Move this over here. Do this there. And then this we can put over here. Make this a little bit smaller. Packed. There. This whole thing a little bit smaller. We can do that. And then we got this. We can put that there. And then that whole thing will make like 60% smaller. And this we'll put boom, boom, boom. Got ourselves a compact little city there. Okay, let's make that a little smaller. Let's take away those lines. Boom. And then we'll make this just a tad bit small there. Boom. All right. Are we back here? So get back into it. Okay. So, what is it that you want me to cover next? Please tell me in the chat. Somebody talk to me. Talk to me, Captain. Okay. Let's see what else we got here. Okay, let's do it. So we went through these. Let's move these here. Try this one. Do it. Let's do some chemistry. We kind of just did some chemistry, so okay. So maybe it's a totally different type of chemistry, but let's do some physics. Just to all know what my repertoire is, you know. We can do the physics, we can do the chemistry, we can do the math, whatever you need. Okay, just put it in the chat, join the Discord, tell me what you need. I'm here to answer homework questions. Alright. Let's do it. Alright, in a Millikan type experiment, two horizontal plates maintain at a potential difference. Okay, so let's get the plates. Perp, thin perp. Okay, so thin plates, and let's spread them apart a little bit more so we can draw in there. And the top one is positive. So the bottom one must be negative, so that's one clue. I think that's going to help us answer the first part. I did have a little quick read of this. Break, just get a little good start. So let's say I drop this. Okay, and their potential difference, they tell us, is 360 volts, and they're separated by a distance of 2.5 centimeters. Okay. A latex sphere. Oh, okay, so this isn't, it's not a droplet. It's a sphere. In there. A little sphere. And it hangs, so let's just say that let's call that M. And the M is 1.41 times 10 to the negative 15 kilograms. Okay, so pretty small. Hangs between the plate. The upper plate is positive. Okay, so the only reason it would hang between the plate, because we know for sure it has a mass, which means there's going to be an FG. So there's only one way it's going to hang between the plates, right? And that's if there's a force pulling it up, right? Balancing that force due to gravity. So what would cause an let's call that FQ, right? Which is the sort of electric force there. What would cause that force? It would be, okay, so let's tone this down a little bit. Way too. Let's do that. Okay. So, okay, so sorry, we would have, yeah, the only way we're going to have an electric force pulling up is if we're attracted to positive, that is if we are negative. So this thing better be negatively charged. Right? So the answer here is negatively charged. Okay, calculate the magnitude of the charge on that sphere. Okay, so let's kind of call that the charge of the mass, yeah, or we could say of the sphere if we want, QS, okay, and that's going to be sort of like, you know, influencing that FQ, so that's going to pop up in that FQ equation. Well, there's a couple FQ equations that we can use, right? There's a couple that we can use, right? And so it's helpful to know sort of what we're looking at here. We don't have two charged objects, two charged little spheres, or two charged little balls, right? 2-point charges is what we call them. We don't have 2-point charges. That would be when we use this equation. 1-point charge, 2-point charge, right? What we have here is we have a electric field that's created by a voltage, right? So V is 360. It's also created by a separation between those two plates, that voltage there, right? So that is actually the equation for the electric field, and we can kind of confirm this. I always like to do this because it has been a quick second since I've done this. So let me just confirm this. This is the force, okay? If we take away one of those and sort of do this, that is the electric field, okay? And so that should look like the voltage. The voltage comes from actually this thing, but only moving it a certain distance, being ready to sort of move it the equivalent distance. Let's just say that that is, okay, so let's just say that this KQ over R is our V. Okay, and so if I divide by another D, then I'm sort of getting back to my R squared. Okay, so I just like to confirm this. If you didn't follow that, that's okay. Okay, this is our equation for a parallel plate to determine the electric field going through that parallel plate, and that electric field is going to be constant. Okay, it's going to be uniform. So that's that there. Okay. Okay, so let's actually, I just want to make this a little thicker. Okay, cool. So let's do it. So 360, and we have to be careful that this is in centimeters. So let's just convert that to meters, and we're good. Okay, so 360 divided by 0.025. Oh god, I'm ghost typing, bro. Way to ghost type, bro. 14. And what is the unit that we're looking for? This is newtons per coulomb. And so now the force comes from the charge that we have on this mass times the electric field that's present there, right? Because that's newtons per coulomb, and so we're going to multiply with coulombs to get newtons. To newtons. So let's just sort of rearrange here, and we could say that QS is actually the same thing as the FQ divided by that E that we just calculated. Okay, and do we know the FQ? Do we know the FQ? We do and we don't. We do and we don't. We don't know the FQ, but where the FQ came from, where the negative charge came from, remember, was that FQ had to be pulling against gravity to oppose it, right? Well, it better be pulling equally, or else the thing's not hanging, it's moving. It's either moving down, or if it's pulling harder, then it's moving up, right? So the thing says that it hangs, which means that FQ is the same as FG. Another way we could sort of like take this back a step is to say that F net Y, F net Y is equal to 0, right? And F net Y would come from FG plus FQ. Well, if that's equal to 0, then one of them is the opposite of the other in terms of sign, and they're the same size, right? And the reason they're the opposite sign is because they're in opposite directions. So we could say FG is equal to FQ, right? Because of the way that we've drawn it. Okay, so that's actually the FG there. It's going to be the same size as the FQ. Okay. So let's just say that on the kind of sly here, that this comes from F net Y is equal to 0. And so FQ, sorry, let's just rearrange this here, and then we'll substitute it. And so FG is just mg, which is 1.41 times 10 to the negative 15 times g, which is 9.81, and divided by, and then epsilon, and that's newtons per coulomb, and this is newtons. So the newtons go away, and the coulombs get slapped up top. Boom, boom, shaboom. And we get, what do we get? One, well, it looks like pretty close to one-ish in some sense. 0.41 divided by 14400 times 10 to the negative 15, and then times 9.81, and we get 9. Oh, wait a second. Doesn't seem right. Okay, so let me just redo it. I got a number that doesn't seem right. It was in the 10 to the negative 15s, but we're dividing by such a big number here that we should get something less than, it should be 10 to the negative 12 or something. So let's just confirm that. So we will do 1.41 times 10 to the negative 15 times 9.81 divided by 14400. There we go. Yeah. So we got the right number, but I suspected I maybe went backwards here. So 10 to the negative 19, and that is coulombs. Right? What is the magnitude of the charge? And that was the magnitude of the charge. Okay. So let's just say this. Okay. Boom, boom. And determine the number of excess or of deficient particles on the sphere. Okay, so this is a multiple, actually, of some value, right? It's a multiple of the smallest unit of charge which you can use is the electron. Okay, so we can't have half an electron or, you know, 3/4 of an electron of charge. We're going to have some whole number of electrons. So I think it's 1.602 times 10 to the negative 19 coulombs. And so N, we can see, let's just get rid of coulombs here. So N, it looks like, is 6. Right? So let's put that into there, and let's say, so the number of electrons, right? And so we are deficient of 6 electrons. Okay? The sphere is deficient of 6 electrons. Deficient. Okay. Yeah, we're at a deficit of 6. Why deficit of 6? Because, wait a second. Negative charge doesn't mean deficit of electrons. It means excess. Right? There, it has an excess of 6 electrons. Okay? Boom. So, just gonna say that this is and then this is B. This is C. Okay, organization's pretty good on that one. Okay, let's keep it going. All right, you, I want you bigger. Let's make you a 48. Hey. Cool. Okay. Can we see that? Yeah, we're good, right? Oh. Okay. I'm just gonna actually crop this just a bit. Okay. Yeah, let's crop from that side there. Beautiful. Okay. Oh, Jill. There. Okay. Everybody. All right. We're good. All right. Okay. So determine each redox half reaction and balance the following equation in acidic solution. Okay, so stepwise, let's do it. So first, we're going to so balance charge on both sides with electrons. Okay, so let's see kind of who is the I mean, really, to do that, the sort of first thing we do is we figure out the half reactions of red and cat. Okay. Red and cat, but red and ox, sorry. Okay, and then we combine them. To balance primary atoms. Okay, by primary, I mean not H or O. Okay. So don't worry about those two, but the primary atoms, we'll balance those. Okay? And we'll balance charge at the same time. Okay? So that'll be our first sort of goal. So let's think about what the half reactions would look like. So reduction and the oxidation. And we only really want, I mean, we're lucky here that we only really have 4. But we only want to consider the things that sort of contain the thing that's getting reduced and the thing that's contain the thing that's getting oxidized. So you'll see what I mean here in a second. Okay. So our reduction and our oxidation. Okay, so who's getting reduced, who's getting oxidized? Remember that Leo says GR, so losing electrons is oxidation, gaining electrons is reduction. So this is gained electrons to the right as we move to the right, okay? And this is lost electrons. So who gained electrons? Well, we have 2 BRs here. And let's figure out what the oxidation states are. So maybe even let's sort of say that's the first state. Oxidation states of everything. Right? That's maybe the first step. So we should start there. Oxidation states of every atom. Okay, so let's do the oxidation states. So oxidation states of the 2 BRs here, because they're bonding with each other, neither is really winning the battle for the electron. So if one was, we would give that one the -1, the other one would get the +1, right? But because they're even, they both get zeros. They're both zeros. They're not winning that battle. The CR, it seems to have lost 3 electrons, so that's a 3+, okay? Here, that's a bonding thing. Let's come back to that in a second. This one has a -1 somehow. Okay? So we should be able to look at the BR and say already that it changed. So let's try to think about whether that's a losing or a gaining of electrons, going from 0 to -1. Yeah? Okay, but let's think about the CR, the chromium, and the oxygen here. So oxygen is almost always a -2. Like, that's a solid place to start. Okay? Almost always a -2. So let's figure out what the math has to be for these CRs so that the whole thing adds up to a total of -2, because we have 7 oxygens there. So what that means is in total there are -14 coming from the oxygen And the kind of question is, what must this be for the total here to be -2? Well, this has to be +12, so that when you add those two, you get -2, right? And there are 2 of those. So how much is each? Well, each one then has to be a +6. So that's how we figure out kind of, we can work backwards, and we can use the oxygens almost always as a rock. Okay, we'll talk about certain circumstances when we don't, but if you want to, you can ask me. Okay, since there's nobody here, I will proceed. So, okay, so let's keep going. So we've got the oxidation states of everything here. Okay, so I'm going to erase this, but that's generally our tactic. Okay. Okay, so this is the oxidation states of every atom. It's in blue. Okay, and then the half reactions. So those half reactions are the transition from any atom that changed from the left to the right. So let's look at the BRs. BR is going from 0 to -1. So is that a gaining or a losing of electrons? Well, that's a gaining. Getting a negative, that's a gaining of electrons, right? So we've found our reduction here. But in order for this to make sense in terms of balance here, we need to say that there was an electron that sort of joined up with this thing to make a -1, right? Do we agree about that charge there? That makes sense, right? The charge on that is kind of -1, and so -1 plus 0 is -1, right? We should look at that kind of like a math sentence there at the bottom, right? Okay, let's maybe just put that in like a purple, a little light purple. Okay. So, let's keep it going. So the oxidation is the thing that lost electrons here. Well, let's just look at the chromium, because the chromium is kind of the only thing that's left. And remember, we don't look at the hydrogens or the oxygens, right? Okay, so what lost electrons? Well, let's just for a second here write down who we have. We have the chromium becoming the Cr2O72-. And I don't care too much about the oxygens there, because the oxygens actually aren't even on the left, so who can even say what's going on there? But these things, this chromium went from a +3 to a -6. So, oh, sorry, not -6. Somehow got erased, right? Because there can't be 2 minuses there, that's +6. So, okay, so that's a loss of electrons, right? That one had 3 electrons missing, and then suddenly it has 6 electrons missing, so it's lost more electrons, right? Okay, so then to sort of balance this out, we have to say that the electrons show up over here. And how many of them? 3 electrons. Well, let's be careful, because we need a 2 here for that to be balanced, right? And then because there's 2, we'll now say 6, right? And now let's sort of balance this. So this is what we mean by balance the charge on both sides, is the last step, and combining the both and balancing the charge. Combine both to balance primary electrons and charge electrons. Okay, so this, we're going to need 6 of these, so we can have 6 of these, and then we can have 6 of these, and then this thing can give electrons so that this thing can take them and use them. Okay, so instead of just giving this off to the environment, it's going to give it to this thing so that it can become this. Okay, and that's a redox reaction. It's kind of like they pair with each other. Hey, you need to You need to lose electrons? I'm looking for electrons. Let's pair up, right? Okay, so then that is what we will combine. So let's maybe even just kind of do this. Let's do this. Let's do this. Let's keep this, 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 and that. So that's kind of before the balancing, right? And this is after balancing. Okay. So this is after balancing atoms and electrons. Okay. And then we combine them and we get 2 Cr3 plus 6 Br2 plus 6 electrons becomes 2. Oh, no, not 2 of those. Sorry. Mike is freaking out here a bit. It becomes 6 of those. Uh-oh. File's getting too big. And 1 of those. Give it to me. There it is. Okay. And 6 electrons. Right? And so the whole point here is that now the 6 electrons can cancel. Right? So we're going to have the same equation, but without the 6 electrons. And now it's just our job there. Okay, so now it's just our job to so this is in acidic conditions. So now we need to balance the O's by adding H2O and then balance the H to the H's by adding H plus, because apparently they're readily available, right? Okay, and we should be able to balance things this way. Okay, so let's add H2O to balance our oxygens. Okay, so let's do it. So we get this. We can just maybe kind of copy paste this a bunch of times here, because this is gonna just add things to both sides. Okay, so here we're gonna add 7 H2Os because we have 7 oxygens there, right? And now we have 14 H's here that we can cancel. Okay. So let's just check that our charges make sense. Okay. So the charge of this is 3, and there's 2 of them, so that's +6. And then this is nothing, so that's total of +6. Here we have -6, and then we have -2, and then we have +14. So does that work? I think that works. All right. So we are done. Right. If we had H2Os or we had H pluses on either side, then we could cancel. But I think we'll just leave it here. Pretty nice. Right. So that was the first step. And then we add, oh, sorry. We add H plus to balance the H's. Okay. Boom. Not bad. All right, let's try switching up. Boom. Okay. And so that is our final answer, I believe. Boom. Let's just double check. So 2 CRs, yes, 2 CRs. 7 oxygens, yes, 7 oxygens, yes. 14 hydrogens, yes, 14 hydrogens. 14 bromines, no. Oh, sorry. Boom. 6, and this has to be a 3. Right. Oh dear, oh dear, oh dear. Good thing we check. Good thing we checked here. Okay, so luckily this is a 0, this is why I kind of got through the radar here for this long, but that's why we have checks. Okay. Boom. So now 6, 6. And then in terms of charge, I think we already checked that. Right? Cool. Okay. Let's keep it going. Who else do we want? Yeah, of course, Samuel. Thanks for stopping in. What's your question? If you want, you can just put it in the chat. If not, you can join the Discord here. Here, let me add the Discord channel here. Hit me with it, Samuel. What do you got? What do you got? Hit me with it. Hit me with it. Alright. Got you. Boom. Right there, Samuel. Can you join that? Is that a link? Or did it like not post as a link? Did it work? Get to me, Samuel. Talk to me. Talk to me. Yeah, dude. Come on in, man. As long as you're polite, kind. Obviously don't get me in trouble. Yeah, man. Come on in.
Hey, can
Hey.
you hear me?
Yeah, man. I got you. What's
Thanks. Look, I'm from Brazil actually, but
up? Okay,
can you help
nice.
me with some questions here?
Yeah, of course.
Okay. Can I call my friends here too?
Yeah, sure, dude.
Okay.
What's the question, dude?
I will send you right now. Wait.
Okay. Oh, we're getting everyone in here, man.
Look. It's in the chat.
All right. Okay, I'm gonna need a translation. So what picture am I looking at? What number?
It's the number 1.
Number
Can
one.
you translate it or you want me to translate it to
I'm
you?
gonna need your translation. Yeah.
Okay. Can you
Here,
push my friend here too?
let
My
me
friend
take.
is in the general chat.
Yeah. One sec.
Okay.
All right. Come on in. Okay, wait. You know what?
Let me just translate it to you.
Okay.
Wait. Are you from UK or United States?
I'm from Canada, actually.
Oh, okay.
Yeah, but I've taught in both places, so I kind of know the school systems around.
I went one time into United States.
Yeah, where'd you go?
Yeah. Florida.
Oh, damn.
I'm going to New York next year, but this year
Nice.
I'm going to Florida again with
Nice.
my mother.
Nice. Where in Brazil are you?
I live in Rio.
Oh, cool. Nice. I have a friend, like a close friend, who's married to someone from Rio.
Rio is beautiful.
Yeah, I've never been actually. I've never been to South America. I've actually never been to New York either. It's one of the places in North America I've never been. But yeah, I've lived in the UK for a while and stuff. So okay, so I'm guessing this is about some tangent circular. I mean, I can maybe try here.
Okay. I'm translating it.
Okay. Hello?
Hey, he can't speak English, but
Okay.
he's just listening.
Okay, sounds good. All right, come on, guys. It's got to be worth a follow, right? Something.
Yeah.
If I can answer
Look.
your question, how about that? Only if I can answer it.
Okay.
Okay.
And the number 1, it's right in the figure, the time that I don't know how to say like physics in English, but I can use Google Translator for you.
Okay. So the time, I'm guessing the time to get from position A to position B is 10 seconds. Is that what it says?
Yeah.
Okay, and then the speed here.
The models.
Guessing that's like tangential. Is that like, you know, when you have this and this, you do this?
Yeah, like number in the letter A, it asks what's the value of the acceleration.
Okay.
Value. Tangential.
Yeah.
Between A and B. And supposed constant.
Okay.
That's what it is. I can send what's writing in letter A.
Sure. All right.
Look the chat.
Okay. What is assumed constant? Okay, so I think like the language here is delicate. Okay, so I'm gonna maybe explain it in English, and you will understand maybe what I'm talking about. Okay, but I'll answer sort of anything you need about this question. What exactly it's being asked, it might be a delicate language thing that might not translate well. Okay.
Okay, okay.
But I think you might be able to understand if I can like kind of tell you everything. You can say, oh, it's that one. Okay.
Okay.
So can I sort of just ask you some questions here about what's being said? This gives me 2 speeds. What are those 2 speeds there? Is that speed and then that speed?
Like all I can say is
Oh,
just
right.
what
Yeah.
is
Okay, wait.
wrong
You
there,
can't
like,
see. You can't see. Here, let me screen share. Let me screen share.
That's okay. That's okay.
Boom. Okay, in the Discord, can you see me?
Okay, I see it.
Okay, so now when I highlight something, can you see it easily?
Yeah.
Okay, so it says 20 seconds, 20 meters per second and 10 meters per second, right?
Yeah.
What is that? So wait, let me just take a picture here of something smaller.
If you want me, I can put in Google Translator all the question, like the whole
Sure,
question.
sure, yeah.
I think it would be better for you.
Okay, sure. This is a unique problem. I've never had it into Portuguese before.
Relax, relax.
I've
It's
done
not
it in
a famous language.
French. It's not what?
It's not a famous language.
It's pretty big.
Yeah.
How many people in Brazil?
Like 200 million people live here.
That's pretty big.
Yeah.
Okay, so that's 10 seconds. The A and B. Okay, okay. I think I can kind of get this.
I'm translating it.
Okay. It's pretty close. So is this object, can I ask if this object is like spinning? Is this just somebody spinning this like around their waist or something? Like I'm assuming because the speed has changed so much, right?
Yeah.
So I'm assuming that this is like, you know, something spinning vertically, right? Because gravity is changing this. Otherwise, horizontally, the speed shouldn't change all that much, right? Well,
Yeah.
really what they're asking us is what is the tangential acceleration? That is the acceleration of this tangential velocity. Right?
Okay, I got it. Look.
Hit me with it. This figure to the side. The time interval lasts between position and 10 seconds. The modules. Okay, got it. Okay.
When it's wrote in like VA, it's because I can't put the symbol.
Yeah. No, that's okay. I get the VA and the VB. But
Okay.
modulus is not a word that we have related in this world, related to any of this stuff. So can you maybe describe to me what that word means, modulus? Can you like describe it to me? And maybe I'll be able to understand the translation.
I can see some other like what it can be in English. So
Sure.
it's like modulus and module. That's
Yeah. Like modules is probably the word that it is in English, but we don't use that word. So like it's like saying like tangential. Instead you could say like diagonal, right? It's like saying we use diagonal instead of saying tangential. So they're not going to look alike in different languages. But I wonder if I can still understand it, okay? Can you tell me what the second question asks?
Wait.
I think I can already start to answer this question for you. Okay.
Okay. I just want this number 1.
Okay, just A, you mean?
Yeah, okay. A, B, and C, but I just you can start with letter A.
Sure.
Explaining it, right?
Okay. So normally when you spin something in a circle, let's assume that like instead of, you know, spinning this thing vertically like this,
Okay.
you spin it horizontally, like you're kind of holding it, you know, and it's spinning horizontally next to you. Yeah? Can you imagine it?
Yeah, I can.
Okay. If you're spinning it vertically versus spinning it horizontally, when you're spinning it horizontally, the speed of the object will not change. So when we catch it here and it's going 20 meters per second,
Okay.
then we catch it here, it should still be going 20 meters per second. Okay?
Okay.
And then we can use this equation
Yeah.
to talk about the acceleration, right?
Yeah.
Okay. I'll have to, no, sorry. V squared over R is just the acceleration, and then mv squared is the force. Okay, but regardless, we can then start to use that equation. Okay.
Okay.
That is the V that we use. That is not the same situation here, right?
Right.
Why? What's happened to the velocity when we see it at B? At B, it's no longer...
It's going down.
It's going down. Well, what
Okay.
what do we call... What do we say when a velocity changes? When it doesn't change versus when it changes, what do we say?
It's not a constant velocity.
Yes, and so it's not a constant velocity, which means what isn't zero? Something isn't zero.
The tangential acceleration.
Yeah, exactly. So AT, right? AC is another thing, but AT is usually zero. It's typically zero, right?
Okay.
But it's not here. So how do we calculate tangential? How do we calculate acceleration just in any world? Or back to, like, you know, just things moving in a line.
You mean like the formula?
Yeah, the formula.
I would triangle something and triangle something.
What does triangle mean? Okay,
Here
so
we call triangle delta, but I don't know
yeah,
how to
that's
say
the
it.
same in English.
Okay,
Exact same.
okay,
So
okay.
delta V over delta T, right?
Okay, all right.
And so it's change in velocity over change in time. So how much velocity has changed over how much time has changed? Well, time has changed by 10 seconds on your clock, and velocity has gone from 20 to 10. So, you know, delta is V2 minus V1, and it's over delta T, and they tell you delta, so it's 10 seconds, and meters per second. So I'm just checking units instead of kilometers per hour or whatever. I'm sure you've been screwed by that before, but it's 10 minus 20, and so it's negative 10 over 10, which is negative 1 meters per second squared.
So this is the final result?
I don't know, you tell me. You feel good about that?
I think it is.
Okay, so I just want to kind of like recheck the question, and sometimes a clue about whether you're wrong or right about an assumption comes from a later question. So can you just tell me what B and what C say, or what they ask?
Okay. I will translate it for you. Wait.
Sure.
Okay, it's right there.
Okay. Okay. So this is something that they ask at A, right? They don't ask you about from A to B. They're just asking you at this one spot. Oh, sorry. It's not that spot, right? But it's where? Here. At that one spot, we have a V squared over R that is our acceleration, right? Our centripetal acceleration. Comfortable with that?
Yeah.
Okay, you feel like you could answer that question?
I don't know.
Okay, so what do you feel not so comfortable about? Let me help you feel better. So what are they like, you know, to answer AC, we need V, the tangential velocity. Do we have that at A?
Yeah, we have.
What is it?
It's 1 negative meters per second It's because I don't know how to say any physics words in English, but
That's okay. That's okay. But
I can write it for you.
okay. But wait a second though. But I asked. Yeah, you're right. You're right. That's the acceleration though.
Yeah,
Right?
it's letter A, right?
Ah. Okay, but wait a second. They asked us for the tangential acceleration, right? This is the tangential acceleration.
Yeah.
Well, that is if I'm kind of moving in this path here,
All right.
that is the, you know, tangent to that. It's this direction, right?
All right.
That is not the same as this acceleration, right?
Yeah.
What is that acceleration? What do we call that acceleration? That is a centripetal. Centripetal. It's the same word.
Okay, the centripetal.
Right? Yeah, that's the centripetal. Yeah, okay. Centripetal acceleration, right? But you knew it was the circular one, right? Yeah? The difference there was just the English to Portuguese?
Okay. Yes.
Okay. So those don't have the same equations, right? Because this one is one that we can use our v tangent squared over the radius. So they told us that the radius was, in the question, they told us the radius was 50 meters. Comfortable with that?
Yes.
Okay. And what is the VT at that spot? At A. What is the tangential velocity, right? That's what V is. What is the tangential velocity?
We still don't have it, right?
We do. We got it from, like, that's where we got our...
Okay. That's what we got in letter A.
Well, it's not what we got. It's what we used in letter A, right? Because look, we said that it was going 20 at A, right? Do you agree?
Yeah.
Okay, so that's all we need. That's the tangential velocity.
All right.
That's the tangential velocity, the 20 meters per second.
So the question gave us...
It gave us it, yeah. So it was kind of just like, it led you down a trail over here so that you would forget that you had it at the start. So that's why they asked you in the second part. So, okay, so then, what is VT here that I'm going to plug into this equation?
20 meters per second.
That's it. What if I had asked you about the AC, the centripetal acceleration, at B? What if I had asked you for that? You're still going to use this equation, but it's not going to be the same value now, right?
Right.
What is it going to be at B?
That's what we are going to have right now. Like,
well, at B, it was at this spot here, right?
Okay. 10 meters per second.
It was 10, yeah, exactly.
Okay.
So you only need it at that one spot, yeah?
Right.
Okay. Can I ask what grade this is? Is this grade like 11? Or do you have grade like numbers like that?
You mean my school?
Yeah. What level?
This is high school.
Okay, how many years of high school?
Here we have 3 years of high school.
Okay.
So it's the first one.
This is the first year of high school?
Yeah, yeah.
Wow, impressive. Okay, so how old are you?
I'm 15.
Wow, nice. Okay. You do this younger than in Canada.
Younger?
Yeah. Yeah, we wouldn't do this until we're 16.
No, but I'm 15.
I know, that's what I mean. You do it younger.
Oh, I do younger.
Yeah. Okay, so what's C? What does C ask?
Okay, let me see it.
Indicate on the figure the centripetal acceleration vector at A. Yeah?
I'm going to see right now.
I think that's what it says. What's sentido?
Sentido is like to where it is going.
Okay, the direction of the...
Yeah, if it's going right, if it's going left, like this.
Yeah. Okay, so indicate on the figure the direction of the acceleration vector at point A?
Yeah, I think it is.
Okay. Cool.
Okay, I have.
It's all Latin languages. You can read them
Okay.
pretty easily.
That's in the chat.
Yeah, exactly. Okay. So, well, I mean, here we go. I kind of already we cheated, right?
Yeah.
But that's the story. So you tell me, which one are they asking about?
What do you mean?
Well, they're saying indicate the direction. I have two directions here. I have up and I have to the right, right?
Okay.
When we compare this to our diagram. Yeah?
Okay.
So which one are they asking about? The up one or the to the right one?
He just wanna know where it is going, like the vector A.
Good.
Yeah. So it's right?
Well, this is sort of like another little thing that's delicate, okay?
Okay.
Because normally the only thing is the centripetal acceleration. Normally the only acceleration is the one that's in the center. So if I was doing this thing horizontally, the only, like, the tangential acceleration, because the velocity wouldn't change horizontally, that would be 0, right?
Alright.
So the only thing would be to the right. Yeah?
Okay.
But now it's not 0. It's there, right?
Okay, it's going up.
Which means there's two accelerations. There's two vectors that have to be added together
Okay.
to give me the result vector, to give me the sum vector. Yeah?
Okay. Alright.
Are you with me on that?
Yeah.
So instead of saying purely to the right or purely up, we have to sort of say up and to the right.
Okay. It's like, let me see how to say it.
Diagonal.
Yeah, that's the same in my language.
Okay, beautiful. Okay. So does that make sense? Is like normally if this was kind of like not this weird sort of slowing down circular motion, that's what this is.
Okay.
If it was normal circular motion, then the answer would just be directly to the right at that spot. And then at the very top, it's directly downwards. And at the right side, it's directly to the left. And at the bottom, it's directly upwards, always to the center, right? That's what circular motion is, right?
Alright.
But because this thing is slowing down, that means that it's not kind of like uniform. This is what we call in English at least, non-uniform circular motion.
Yeah, it's the same right here, like non-uniform we call.
Okay, perfect. So non-uniform circular motion, which means it's not, you know, like what we said, this is not 0, right? Like that's the perfect world of circular motion. The tangential acceleration is there because it's slowing down, right?
Okay.
Oh, wait a second. I lied to you, right? Because what did we say? I said that this vector was -1 meters per second squared.
Yeah, that's what you got in letter A, right?
Yeah, okay, but can I ask the direction of it? Was it -1 meters per second squared up?
No, down, I mean.
Okay, yeah. Oh, well, are you turning the negative up into down? Is that what you're doing when you say that?
Yeah.
Yes.
I think it is.
Yeah, exactly. Right? It's
Okay.
it's slowing it down. So this is actually a vector that's in the opposite direction, right? Yeah.
Okay.
So I lied to you. So negative up is down, right?
Right.
Okay. So then this is 1 meters per second squared down. Okay. Boom.
Okay. So
then it's not up and to the right, right? Because up and to the right was from our up direction. That's what we have to correct. Yeah?
okay.
So it's not up and to the right, it's what?
It's just up.
No, because look, there's no, if I have somebody pushing on me to the right and somebody pushing on me down, which direction am I going to go?
Down.
Nope.
Down to the right.
Yes, both, right? Down and to the right. So this is my result vector here, right? Or let's maybe just kind of highlight like that, down and to the right. Yeah?
So we got down to the right in letter C. That's it.
Yeah,
I think.
so that's how I would draw that direction vector there. I would draw it like down and to the right. Okay. And I would maybe even tell them that I'm kind of like, I'm not crazy. I'm sort of saying that's the acceleration to the center. And then this is the tangential acceleration.
Okay.
And together that makes up the triangle that you see there, right? Like, you know, that triangle kind of vector stuff.
Yeah.
Okay. Yeah. So I would maybe like draw my final answer like that and sort of say that was my final answer there. That's the acceleration.
Okay, that's good.
Cool. Do you feel like you understand it?
Yeah, I think.
Okay. Do you think you can explain it to your friends?
Yeah, I think yes.
Yeah. Okay, good.
Yeah.
That's about as good as you could do, right? Like if you can explain it, and honestly, a good practice for you to test your understanding to see how much you understand it is to explain it to your friends. Okay?
Yeah, yeah.
Because they'll ask you the questions you're like, "Oh, wait, I don't know." Or like you'll have to sort of, you can't just repeat what I said to you, right?
All right.
But you're also translating too, so you can't really, there's more
Yeah, I know.
there's more, it's more difficult. Okay, awesome. Thanks very much, Samuel. I appreciate it.
Thanks. So, let me just see what I got. Like, what I got in letter A is just I don't know how to say it. Like, -1 meters per second to square. We call it square here.
Yep, yeah.
Okay.
1 meter per second squared. But wait a second. Remember, that was up,
Okay.
right?
But when I answer it, I just need to write or I need to draw?
No, I think you're just writing it, right?
Just write. So I don't need to say it's up or down.
Yes,
It's
because
just
it's
my
tangential, right? Because it's like around the circle, right?
So I just say it's -1 meters per second to square.
That's what I would say. Yeah, that's what I would
Okay.
say. Yeah.
Yeah. Letter B, I got 10 meters per second or 20 meters per second. I forgot it.
No. I don't think we actually finished part B, right?
All right.
Because we got to this stage. Yeah?
Let me see here. He asked for the value of centripetal acceleration in A. That's what he says in letter B.
Yeah, exactly. So the centripetal acceleration, remember the equation was the tangential velocity squared and then divided by the radius. And they told us the radius. And you
So
said, go ahead.
It's 20 meters per second and 50 meters.
Yeah, and we have to combine those into this equation, right?
All right.
So 20 squared divided by 50. Yeah?
Yeah.
And then the third one was, yeah, just our drawing, right? And this is how I would really draw it. Okay?
Okay.
Cool.
So I just need to divide it.
Yeah, this one here. Yeah. Yeah, exactly.
Okay.
Okay. All right, I want you to update me on how your explanation goes to your friends, okay?
Okay.
Okay. Tell me in the chat.
Let me just see what I got in letter C is like I just need to draw it down to the right?
Yeah, exactly.
So I need to draw in this answer.
Yeah, exactly. They said indicate in the figure, right? Draw it in the diagram. So I think they want you to just draw right on the page. I mean, if it's digital, then I don't know how you're gonna do that, but maybe just copy and paste it onto your page or something. I don't know, or draw it yourself, maybe.
Yeah. I can do it by my hand.
Okay, yeah, perfect. There you go.
Okay. Thanks.
Cool.
Thanks.
Yeah, no problem. Stop in whenever you need some help. Okay, this is my bread and butter. Do you have that phrase? My bread and butter?
Yeah, okay.
Okay.
I think it's like, I don't know.
It's the same thing. It means it's my wheelhouse. It's easy for me. Okay, it's fun
Okay.
for me too.
Okay,
So okay,
you helped me a lot.
cool. Okay, awesome. Yeah,
Yes.
anytime. That's what I'm here for. All right, if you want the notes from this, I'm gonna I can make it available to you. You can email me. Okay, here
Okay, okay.
or I'll put them in the Discord. Okay. Here,
That's okay.
I'll make a channel here. Notes from stream. Boom. All right. Okay, we'll see you again soon, Samuel. Thank you.
Okay, thanks.
All right.
You helped
See
me
ya.
a lot.
Yeah.
Have a good day. Bye.
Yeah, you too, man. See ya. Boom. What we're here for. Okay, let's make this more obvious here. All right, Ivan, thanks for stopping in. Ivan Kozlov from VUM today. I don't know what that means, but thanks for the message anyway. Appreciate it. All right, let's answer some more here. We got more? Yeah, come on. Close down the disk. Struggling, it's probably hurting us a little bit. There we go. All right. I think we do a little bit of physics then. Let's maybe do this. Let's do that. Boom. Boom. All right. Gotta get a new page. This thing gets pretty slow if we put too much on there. I'm just grabbing a new question here. Boom. Boom. Let's grab some physics questions in honor of our friend Samuel. Thanks for stopping in the stream. Hey, did you follow? Did I help you? What in the heck? You got away with that one. Pulled the veil over. Pulled the veil over there, Samuel. How'd you get me like that? Alright. Let's do it. Boom. Okay. A rescue pilot wishes to drop a package of emergency supplies so that it lands as close to as possible to a target. If the plane travels with a velocity of 81 meters per second and is flying 125 meters above the target, how far away horizontally from the target must the rescue pilot drop the package? Okay. So I think I understand here. We've got ourselves a little plane. Okay, so now this is going to be a test here. Not bad, not bad, not bad. Impressive, impressive, impressive. Alright, beautiful. Okay, so this thing has got a package. And it's gonna drop. Okay. And assuming this thing has a velocity here, so this thing has a velocity in that direction. So this thing is going to kind of land somewhere where there's a target. Let's just check the interpretation here. Okay, so they wish to drop package emergency supply so that it lands as close as possible to target. If the plane travels a velocity of 81, okay, so that one there is our 81. So let's just make that black, 81 meters per second. And it's flying, so the package, let's say, is 125 meters. How far horizontally from target must the rescue pilot drop? Okay, so it's asking kind of this distance here. What is that delta D in the X direction? How far away from the target must it drop it? Okay. Okay. So let's do it. So the plane and the package are both going to have the same velocity, right? So what I'm going to do is just kind of break things down into the X and the Y. So the velocity in the X of the package at this spot, we're going to call this spot, let's call this spot, let's call this spot 1 and this spot 2. Okay. So Vx the whole time is 81. Okay. And D1 is 0 meters. So we're going to call this the kind of 0 spot. And H1 is 125 meters. So that means that the starting spot is 120 meters above this spot here, which we're going to call the 0 spot. So that is the vertical. So sorry, let me put that here. Okay, so here D1 and then D2 is still the X's concern. And really, that's the question we don't know. How far from that 0 spot are we, right? But delta T, which comes from T1, we don't know that either. Okay, so that's going to point, those both kind of point to the vertical. So let's figure out more about the vertical. So V1 in the vertical, V2 in the vertical, A in the vertical, delta T in the vertical, and delta D in the vertical. Okay, so I'm also just going to change this D1, D2 to be delta D. Okay, and we don't know that. Okay, so let's kind of shift to the vertical here. What do we know? So delta D is actually going to be our H. So let's just use H here. So we can say delta H is positive or negative 125. That's a question we have to ask. Hey, Samuel says, hey, can I ask you later 2 simple questions, just interpretive questions? Yeah, for sure. Yeah, put them in the Discord, and after this question, I'll see if I can help. Okay. Now I'm an international professor. Yeah, there we go. Boom. Put it on me resume. Thanks very much, Samuel. You're opening doors for me. Okay, so yeah, put it in either the questions channel or the general channel again. Okay. But thanks again for sticking around. Okay, so I'm gonna say that this actually is down is negative. Okay, I'm just gonna stick with that. It is gonna make my life harder, but it is generally a little easier to understand. And to the right is positive, okay? And to the left is negative. Okay. Okay. So let's say the velocity at the 1 spot horizontally is 81, but vertically it's 0. It's not moving up and down at all, right? And 2, we don't know what it is, but we don't necessarily need to know what it is because we do know the acceleration. So H, sorry, let me just change that. It lost height, so its height went down, so it's 125, negative 125 meters. Acceleration is negative 8.1 meters per second squared. That's gravity. And the time we don't know. But we now have 3 of the 4. The whole goal here is to have 3 of the 4, and we can solve for the 4th. So what I want to do, the fastest way is going to be to solve for time. Time in the horizontal and in the vertical are the exact same, so I'll be able to sub it in here, and then I'll be able to use these two to solve for this. Okay? So my plan is, let's take our vertical things here. Let's take all 3 of them. Solve for t, use it in the horizontal to solve for d. Okay? So, okay. So, sorry, let's do it. So I'm going to use the equation that doesn't have v2 in it. So that is delta d, or in our case, delta h. So delta h is equal to v1 delta t plus 1/2 a delta t squared. And unfortunately, I think this is going to provide some quadratics, but maybe not because the v1 is 0. So that goes away. That's 0. And so negative 125 is equal to 1/2 of negative 9.81 times delta t squared. And so let's just solve here. Rearrange and solve. And we're only going to look at the positive time. We can tell you kind of what the negative time means, but for now, let's just only look at the positive time. And so, 125. And so, we're going to do the square root of 25.48. And we get about 5 seconds, so 5.05 seconds. Okay, and that is our delta t that now horizontally is the exact same time, okay? And so that is how long you were moving horizontally, and that is the speed you were moving horizontally the whole time, and it was a constant speed, so that means Vx is equal to delta d over delta t. And so delta d is Vx times delta t. We can do a little rearrange there, and we can solve. Okay, so let me just kind of call this delta dx because I called it delta dx there. Okay, so then I get 81 times 5.05, and that should be what, like 106,600-ish, 1,700-ish. Totally wrong. 409, that's why we plug it into the calculator. So let's just say 409, and that is meters. Boom. Okay. How far away horizontally from the target must the rescue pilot drop the package? 409 meters. Because it's going to take that long to drop, right? That height. And so moving at that speed, let's go back kind of that amount of time. Yeah? Okay. Sorry, you might get a little bit of Nightbot spam. Sorry about that. All right. So what do we got? Give it to me, Samuel. You said you had a question. Do you want to jump in the Discord again? An interpretation question, you said. Hit me with it. I can't believe it, Samuel. You're listening to Spotify at this crucial time. At this crucial time. Okay. I'm gonna give you about 10 to 12, and then I'm gonna move on. Move on. We can get this one going though. Boom. Okay. Okay, actually, I'm just gonna take a little banana break here. I'll be right back. All right, keep it going. Okay. Done my banana. Thank you for your patience. All right. I'm just gonna put a little message up. Samuel, ask your question in Discord. Or join a channel. Boom. Okay, and let's just pull up the boom. Okay. We're good. Okay. Cool. So consider an example where a small, fast-moving hover puck of mass 2 kilograms collides with a large stationary hover puck. Friction is small enough to be negligible. Okay. Okay, and they're asking us all these things. BA1X. What? What is A1, B1? Okay, wait. Mass of A, B, large stationary hover puck. Okay, B, and then 1X, 1X, 2X, 2Y. Okay. Let's see. So why is there only A? They go off together. Large stationary hover puck. Okay, so they're, I guess, not asking us what the velocity of B is afterwards, because they only ask us about A. Sure. Okay. Okay, so let's do it here. So we're gonna need to use momentum. Okay, so let's say that momentum total in the one circumstance is going to be the momentum total in the two circumstance. And the momentum in the one, they each have their own x and y. Okay, so there's an x version of this equation where the x's are equal to each other and then the y's are equal to each other. Okay, and each one of these come from mass A and mass B. Okay, so mass A 1, sorry, let's maybe make this a little nicer. In the one circumstance, the AX, no, that looks like this isn't great. Mass A1X times V1X or V A1X plus, and then this whole thing is going to just get nasty and ugly, right? So, okay, wait, we got some new people here. Hey, okay, you sent it. Okay, yeah, okay, let's take a look here. All right, so Samuel has added, a new question. Okay, so let's see. See if we can just do this. Pow. Okay, we'll come back to this question. Let's get to the viewer questions. That's what matters. That's what really matters. All right. Amber, come on up here. Up here. Okay, a figure represents the trajectory k. Which of the vectors indicates that can represent its acceleration if? Okay, so the grammar is a little different, but I'm guessing maybe I can even just do a little interpretation here. Is the motion uniform, is moving retarded, and is the motion accelerated? Okay. So, is the motion uniform? A figure represents the trajectory of a particle from A to B. From B, right? Can I just ask, is this going from A to B, or is this from B to A? I think this is from A to B, I'm guessing. So this is a particle moving from A to B, right? And it's asking, what is the acceleration vector, right? Okay, well, what causes motion like that? What causes circular motion? What causes circular motion? It's a vector that is always pulling towards the center, causing you to curve perfectly along a circular route. So anytime you do circular motion, you have a circular or central acceleration, right? Uniform circular motion is well, what is it asking? Why is it asking like 1, 2, 3, 4, 5, 6? Is the next question ask about 1, 2, 3, 4, 5, 6? Okay, but then it says, is the motion uniform? So it doesn't quite look like this is actually like a perfect circle. So I don't know if it's kind of asking that. Like that looks like a little bit sort of oblong, right? So my perfect answer to this is like not perfectly circular. So not uniform circular motion. That's kind of like if I was being really picky. But that's pretty close to a circle. You know, it's not perfect, but it's pretty close, right? Okay. And then it says I think, so this doesn't translate well. Okay, it's actually a little bit inappropriate. Is the motion accelerated? So I think there, like, I'm sort of asking, is there an acceleration? That's what I think that question is. And if it's doing this kind of circular motion, or if any object is changing its direction, even if it's just changing its direction, that's enough to say that there's a circular motion. Okay. So, sorry, that's enough to say that there's an acceleration. So is there an acceleration? Yes. I think what this is sort of asking is a little bit tough to answer. It could be asking, is it slowing down or is it speeding up? Okay, the figure represents the trajectory of a moving particle from A to B. Okay, so that's kind of like, you know, that's helpful, but it's tough to tell, first of all, if it's perfectly uniform, but also I'm interested to sort of what this, you know, 1, 2, 3, 4, 5. I'm guessing it's kind of like you have to guess which one is the acceleration vector. And then, yeah, it's not perfectly circular, so not perfectly uniform. Okay. Can I just I'll check what the first question was here, or what the other question was. Oh, okay. No. I see what it's asking. Okay. The question is asking you to pick one so that you have uniform motion. Pick one so that you have movement, so that your speed slows down, and pick one so that your speed slows up or speeds up. That's what I think is being asked here. Okay. I think you have to pick one of these ones. Yeah. So that's kind of my guess here. So if that's the case, then these aren't kind of yes, no questions. These are like pick one so that it works. So if it's doing perfect circular motion, then at that spot, it will be pointing perfectly to the center, right? And so that is number 3, right? If you want the speed to slow down, well then I could pick really either this one or this one, because that is kind of going against the grain of my velocity vector. So that will be, if that's the acceleration and that's the velocity, that will slow me down, right? So I kind of want to point it back in the direction of the velocity, at least a little bit. So either V or that, okay? I think that's kind of what this is asking. This, I think, is asking kind of like the like really this thing wouldn't move in this direction if the velocity was this, right? It would just continue like this, and it would just slow down and stop here, right? So we would actually see whether it was curved or not. So I'm actually going to say it's 4 here, because then or else it wouldn't curve backwards. It wouldn't curve back towards B. We still need a little bit of left motion is my argument there. Okay. And then is the motion accelerated? I think this is asking like so that I can speed up, and that same argument for number 2 there. That would be my guess for those. Okay. Kind of hard to say because there's, you know, there's a few barriers here, but we're doing our best. I think that's kind of like the best way I could answer those. Yeah? I hope that helps, Samuel. Okay, let me do this. Okay, put you there. Okay, and put this here. All right. Boom. Okay. Okay. I hope that helps, Samuel. Let me know if you're still kind of struggling. Of course, I'm more than willing to help. But okay, and you saw that. All right. Boom. Okay, so I'm just going to jump back into this. So this we're doing the sort of before. So I'm going to maybe just signify this instead of with a 1 and a 2. I'm going to signify this with a prime. Okay. Prime meaning after. So any prime means after. Okay. So instead of 1, I'm just going to say the mass of A times the velocity in the x of A plus the mass of B times the velocity of B in the x is equal to the mass of A times the velocity of A in the x prime, so after, plus MB. You see the kind of pattern here, right? And that story is going to be the same for the vertical. Okay, so this shouldn't say X, this should say Y. Okay. Okay, thank you a lot. I'll answer W342. Yes. Okay, awesome. Samuel, I'm glad I could help. Okay, and please, please, please try explaining it to your friends, because that's an awesome test. Yeah, and if you're still struggling, feel free to jump in the Discord, let me know, or whatever it is. All right, appreciate you stopping by. You can come back soon. Okay. So we're going to do almost the exact same thing, but in the Y direction. So now, to answer all these questions, we're going to need a little inventory of all of these different variables. And we'll see if we have any clues about any of them. Okay? So this is our setup, okay? And let's just see what they tell us. So they tell us the mass of A is 2 kilograms, and the mass of B is 4 kilograms. And friction small enough to be negligible. Okay, that's good. And they tell us that VA is 6 meters per second, and we're going to say to the right. Okay. And they say VB is 0 meters per second. Okay, so that's nice because that means that this is going to cancel out, this is going to cancel out, right? And VA is purely to the right, so actually VAY is 0, right? So that whole side is 0. Okay. And did they tell us anything after? Yeah, they tell us VA prime is 2 meters per second. And how are we going to represent this direction? Well, it's north. Oh, so we shouldn't say right, we should say east. They did put a compass here. So it's north 30 degrees west. Right? So that we're going to have to separate into a so that is going to be VAY prime, and that is going to be VAX prime. And we will use those. Okay? So this here is 60. And this is 2. Should be enough, right? So VAY prime is the opposite in the hypotenuse, so that means that it's 2 times the sine of 60, and VAX prime is 2 times the cos of 60. Okay. Okay. So 2 times the sine of 60 is let me maybe just throw this here, that a tad bit smaller. Alright, beautiful. Okay, if you have questions, feel free to jump in the Discord. We just had Samuel, we were answering some questions of his. Yeah, Samuel, I should still be online, so come on by, bring your friends, alright? You got to drop a like, drop a everything. Alright, drop it, smack it, slap it. Alright, you know the drill. Come on. Okay, yeah, I can help you with some chemistry. For sure. I can't help you with the Portuguese though, unfortunately. Come on back. Okay, and that is meters per second. And this one here, 2 times the cos of 60. It's 1. So, yeah, cos 60 is half, so then that's 1 meters per second. Okay. So, and then VB, we aren't really told about VB. Okay, so let's maybe just kind of, let's maybe kind of do some plugging in here. Okay. So, 2 kilograms. VAX, we said is 6. Alright, sounds good. Okay, so we said that was 6, and that means to the right is positive. Ooh, okay, so VAX, so this should be -1, because we've made to the right positive. And let's make up positive. We did make it, I think, actually. Okay, so that's -1. Okay, so that... let's do this. 2 times 6 is equal to 2 times VAX 1 prime is -1, and then plus MB is 4, And VBX, we don't know that, but now we can solve for that. Okay, so we're going to solve for that there. Whoa. VBX prime. Okay. Okay. So okay. Okay, right? Yeah. Okay, so VB is so that's what? 12 plus 2 divided by 4 is 14 divided by 4, 3.5 meters per second. And let's just make sense of that. That should be in the positive direction because this one was negative. So then this one has to kind of make up for it. So it should be in the positive direction. So that means it's to the right. Okay. Or east, sorry. Okay. So that's VBX. And then VBY prime, we're going to get from this equation to VAY is positive 1.732 plus 4 VBY prime. And we get VBY prime is negative 2.732 divided by 4. And it makes sense that this thing is negative. So 1.732 divided by 2. So negative 0.866. And that's meters per second. And that was north, so then that's positive south. And it makes sense. If nothing is moving up and down and suddenly you're moving up, I better be moving down, right? So this better be moving down. Hey, I'm Sales Fan. Thank you a lot. Yeah, no problem. Hey, awesome. Thanks for stopping in. Appreciate it. You guys, you all just watching, and you know, just hanging out. It helps. And feel free to come by if you have any questions. I know that, you know, Samuel might be your English connection, but yeah, I mean, I'm more than willing to help. Okay, if he's willing to help us translate. All right, thank you. Okay, so we got VBY, and so what are we doing here? So we're done, I think, right? We got everybody? I think so. Yeah, we got everybody. Boom. Ba-ba boom. Okay. Not bad. Should we try some chemistry or what? What do you think? Yeah, I think we can do some chemistry. Come on. Let's do it. Okay, so let me just put the veil of darkness. Okay, and then let me pop this on for size. Boom. Boom. Okay, we're back. Calculate the pH of a sample of vinegar that contains 0.83 moles per liter of acetic acid. What is the percent association of the vinegar? Okay. So, the test here. The test. And actually, I think we can't do this question without our dissociation constant for acetic acid. Okay, so the Ka is 1.8 times 10 to the negative 5. Okay. So let's do it. So first, we're going to say that we sort of add 0.83 moles per liter of the acidic acid. Okay, so I'm just going to represent it like this because what's important is that we get an H plus and an AC minus, right? Well, the question is, if I add that concentration of this, does all of it separate? In which case, you know, the concentration of both of these will be 0.083? Or does only some of it dissociate? And that question gets answered with this association constant, okay? So that's sort of like what we're going to do. We're going to do what's called an ICE table, okay? So let's just kind of use this, put this here, we'll do this, put this there, bada boom, bada bam, bada beam, bada boom, okay, boom, and we'll shoot, bam, and we'll do this, and a boom, and a bam, okay, and a boom, and a bam, okay. So we don't really know how much of each of these we, sorry, to say initially, we're going to just say that we kind of add that thing to the solution, but it's the acetic acid. And so at equilibrium, after a little while, some of it will have separated, but some of it will still be in the form that it's in now as acetic acid, as HAC, okay? And so we have to sort of say, well, it's going to go down by some amount, and the amount that it's going to go down by is the same that those two are going to go up by. And so this one, after that change, will be equal to this. And after the change, that one will be equal to X. And after the change, that one will also be equal to X, right? And what this says is the Ka is the equation that we have here. It is the H plus and the AC minus over the HAC. So we can kind of come up with this quadratic equation here, okay? So we're going to get x squared all over 0.083 minus x times 1.8 times 10 to the negative 5, okay? And actually, what's nice is our x amount that this is going to go down by, the amount that this is going to change by, is, okay, wait, you can't see that actually, so let's just make this all a teeny bit smaller. So the amount that, like, you know, from 0.083 minus x, if that x value is 0.0000001, you're not really going to notice that subtraction from 0.083, right? So it's important that we kind of compare this, but that k value basically tells us who is being favored. Is it products or is it reactants? And we know that for the most part, a lot of this is going to stay in reactant form, okay? And it's going to stay as HAC, which means this x value isn't that high. There is a technical term for kind of what we're doing here, and this is, you know, what we do. And if this is bigger than 100 times bigger, so if 0.083, the initial amount, divided by the k value, which is this, is bigger than 100, then you're okay. And that's basically, that's true in this case. So we're okay to just sort of assume that that's so insignificant to the size of 0.083 that it's the same, it looks the same as this equation. As if the x was never there. On the bottom, at least. Yeah? Okay. And so, wait a second. My big old head's getting in the way. All right. So we can just say this. So I'm just going to say here, x is significantly smaller than 0.083. the initial amount divided by the Ka is bigger than 100. Okay. So then we can assume that we're safe to get rid of the x there. Okay? And so we can solve x is what? X is the square root of 0.083 times 1.8 times 10 to the negative 5. So 0.083 times 1.8 times 10 to the negative 5 is some crazy number, and then we square root that and we get 0.001. Okay. And so, okay, so that's our x value, and so our pH is the negative log of that H plus concentration, which is the negative log of 0.0012. Okay, so we get 2.913 is the pH. H plus concentration that we said was the x value, so it's equal to that. Okay, and so the negative log is this. Boom. Not so bad. Not so bad, mate. Okay, so let's maybe just make this nicer. Do this. Boom. Okay. All right. Let's just check the Discord if there's anything there. I don't think so. Okay. Let's keep it going. Let me grab a chunk of questions here. Okay. 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 We got ourselves some questions here. Some questions. Alright. Might have to take a little eat break. Oh, it's so great that I could help Samuel and his friends. Okay. Sorry. Boom. Boom. All right. Okay, so similar kind of question here. The base dissociation constant, Kb, for quinine is 3.3 times 10 to the negative 6. Calculate the OH minus concentration and the POH and the pH of a 1.7 times 10 to the negative 3 moles per liter solution of that. Okay, so we're going to start. We're going to sort of quinine. So this is an acid. No, this is a base. Okay. So that means that there's some sort of quinine H. Or no, let's interact it with water here. So H2O plus quinine becomes OH minus and H quinine. Okay. And they put, so this here, we're not going to have to worry about this because it's water. It's a pure liquid. Okay. Everything else has solutions or has concentrations, but there's no concentration of pure water. Okay. So ice means initial change equilibrium. Okay, so initially we have 1.7 times 10 to the negative 3 moles per liter. Yeah, this is always in concentration. Okay, here we didn't add any of this concentration. Okay, and we didn't add any of this concentration. We only added the first one there. So what they're going to say is sort of like, you know, move this thing to its equilibrium. And so this is going to go down by a certain amount. So we're going to say minus a certain amount x. Whatever that goes down by, that will go up by, and that will go up by, each the same. Right? And so just like the last question, we can sort of do this. We can say minus x, and then this is x, and this is x. So those are the concentrations at equilibrium of each of those things. Okay? And the Kb comes from the products of this equation. So this is going to be x squared over 1.7 times 10 to the negative 3 minus x. And the Kb for this thing is 3.3 times 10 to the negative 6, which is tiny. Okay, so it's 10 to the negative 3 to 10 to the negative 6. So it's about 1,000. It's actually about half 1,000 times smaller. So it's okay to do that same assumption. Okay, so we're going to do the same assumption, right? Same. Let's maybe do this. Same assumption. Okay. So we can get rid of that minus x, and we get x squared over 1.7 times 10 to the negative 3 is equal to 3.3 times 10 to the negative 6. Okay. So x is the square root of 5.61 times 10 to the negative 9 and then that square rooted is C, and this is kind of what it relied on, right? X is tiny, right? Sorry, it's 0.000075. So that is 7.5 times 10 to the negative 5 moles per liter. Right? Okay. So, okay, so then, yeah, so then the POH, or really they ask us for the OH minus concentration, and so that was the first thing that we found, the 7.5 times 10 to the negative 5 moles per liter. And now we can find the POH from that number. It's the negative log of that number. So it's 4.13. That's the POH. And remember that the POH plus the pH always equal 14. Right? No, you can't see that. The POH and the H always equal 14, so then the pH is 14 minus 4.13. Okay. Let me actually do this. Let's do this, do this, do this. Okay. So 14 minus 4.13 is 9.87, which makes sense. It should be pretty high on the pH scale, right? Because it's a base. Okay. We did it. Boom. Okay. Let's keep it moving. We got math. All right. So to factor this, we need to do factor theorem, which is basically f at a equals, if f at a equals 0, then x minus a is a factor of f of x. Yeah? That's the foundation of this, right? Okay. So let's keep it moving. What do we got? What do we got? So that means we have to try to guess a number that when we plug it in, we get 0. Okay? That's going to be the start of this, unfortunately. We can get some guesses from the back number. So I'm going to try 2. Actually, let's try 1 first to start off with, because these numbers are pretty nice. Okay, so 1, 3, minus 1, minus 27, minus 18. It's always worth it to sort of try this. It looks like this is a problem, minus 18, minus 27. So I'm going to try negative 1 and see what happens. So negative 1 to the power 4, I get positive 1. Plus negative 1 to the power 3, I still have a negative, so then that's minus 3. And then negative 1 squared, so that's positive, so then that's still minus 7. And then negative 27 times negative 1 is plus 27. And then minus 18. Oh, this might work. Okay, so let's see. It looks like it does, right? So 28 minus 28 is 0. So this is f at minus 1. F at minus 1 is 0. So according to this statement, x minus negative 1, which is really x plus 1, is a factor of f of x, if we call this f of x. Okay. Cool. What is this? I don't get this spam. I guess it's good that you're coming in and you're typing, but bomb red sister 19 lol online. I'm gonna ask you to stop, but I don't really see the harm. So I don't know. I'll just hold you to it. Okay. But thanks for stopping in. Thanks for your input. Appreciate it. Okay. So let's keep going. So x plus 1 is a factor of f of x. Oh, we don't have any music anymore. That's what's different. Okay. Okay. Cool. Let me turn this down just a little bit. Okay. So, okay, so x plus 1 is a factor. So that means that we can do some long division, baby. This is going to be fun. Oh, to the 4. Okay. Boom. Okay. Okay, so let's do it. So I'm going to kind of do this, the slow and the long here. Okay. So we'll just write these down to be able to do it this way. Okay. Okay. So first question is kind of like, what would we need to multiply by x plus 1 to get an x to the 4 term? And it would have to be an x to the 3 term, right? It would have to be an x to the 3. So let's multiply the x to the 3 by both of these, and I get x to the 4 plus x to the 3 plus 1x to the 3, right? That's what happens when I multiply them, right? And then I subtract these two, and the reason I subtract them is to try to get rid of that, right? So let's subtract the 2, and I get 3x cubed minus an x cubed. I get 2x cubed. And now this is something that I can kind of bring down, and I'm going to kind of just do the same thing all along, okay? So here, the question here would be, what do we kind of write down, or what's the procedure here? We're going to take this number, so we're going to take this number, we're going to multiply it by this number here, and we're going to write it down here, okay? And then we're going to subtract the 2, right? So we end up getting 2. And look, that number and that number are what we got here, okay? So let me just kind of erase this, and let me just say 1 and 2, and let me just say 1 and 2. 1 and 2. Okay? Okay, so let's keep going. So what times x plus 1? What would I have to multiply x plus 1 by to get, just for now, just to get a term that has 2x cubed? Well, it would have to be 2x squared, because then this x would multiply by the squared to give us a cubed, right? Okay, but now when I multiply that by the whole thing, what happens? So now 2x squared, what happens? Well, hopefully I get what I was looking for, but then it also expands to the +1, right? So then we also have plus 2x squared, right? And so that's where this next step comes in. We multiply the 2 by the 1 and we get a 2 here. And then we subtract these two. So -7 minus 2, we end up -9, right? And that's what these numbers are here. So that 2 and that -9 are that 2 and that -9 there. All right. Thank you for your today message. Appreciate it. I'm gonna have to say that I mean, I don't know. Go ahead. I don't even know what this is, but go for it. Okay. So -9x squared minus 27x, and now I have to ask the same question, right? So let's maybe do it in this one. So -9 times 1 is -9, and then when I subtract those two, what do I get? I get -27 minus 9, I get -36, right? So that means that what I should get here is -9x squared minus 9x, and then I should get -36x, right? Oh, wait a second. -27 minus -9 is +36, right? Or is +9, right? So I shouldn't get -36x. I should get minus, what, 18x. Minus 18x. Right? And then what do I do again? I multiply that -18 by the 1, and I get -18, and I better get 0. So this is my, this here is proof x plus 1 is a factor. Right? Remainder equals 0 is proof it's proof, and so yeah, so the answer here is -9x minus 18, and the remainder of 0 is the proof that we needed that x plus 1 is a factor. Okay. Okay. Cool. So from there, we now still have to factor this. So we could say that this whole thing that is equal to that times x plus 1, but then we still have to factor this one. Okay, so we're going to do the same thing. So let's think of a number. So we have to, again, try to think of a number that we can plug in to get 0. So I don't think 1 is going to work because we have 1, 2, 9, and 18. So that 18 is bigger than anything else. So I think I'm going to try 2. I'm going to try 2. So 2 cubed is 8 plus 2 times 2 squared is 8 minus 9 times 2 is minus 18, and then minus 18. I don't think these two should be the same sign, so I think we should try -2. So let's try -2, see what we get. So -8 plus 8 plus 18 minus 18. That looks pretty good to me. So that's f at -2, and that's equal to 0. So x plus 2 is a factor. Okay? So that means that we can do the same sort of division. X plus 2. Let's see if we can do this one purely the fast way. So we're going to put 2. We're going to put 1, 2, just the coefficients for each one. -18. This one we start with a 1. Okay, now the procedure is take this, multiply it by this, put it here, and then subtract these two to get your new one. Okay? So let's do it. 1 times 2 is 2. We put it here, and then we subtract those two, and we get our new one. It's 0. Okay, that's going to be important. And then, so let's just do this. 2, and then that's 0. Now 0 times 2 is 0. And now -9 minus 0 is -9. And so -9 times 2 is -18. And then when we subtract those two, we get 0. And that's good. Right? That's good. Because that means the remainder is 0. Okay? So that's a good thing when we do that division. Okay, and now that is basically our answer with the appropriate terms, but we wouldn't write it like that. We would write it as just x squared minus 9. Right? And now that thing can be factored pretty easily. That's a difference of squares. So there we go. Okay. 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 So we can rewrite this statement here. And this is x plus 3, x minus 3, and x plus 2. Right, and we can do a quick check by just multiplying all these numbers out back, and we do get -18. So, not bad. We're in pretty good shape here. Okay? Okay. Okay. Beautiful. Okay, let's grab one more here. Let's do a little physics here. And then we'll maybe take a little break. Okay. Okay, so a pebble is fired from a slingshot with a velocity of 30 meters per second. It's fired at an angle of 30 degrees to the horizontal. Okay, so the slingshot was here. And it shot off. That's the velocity of 30 meters per second. And it's at an angle of 30 degrees. Is that right? Is that how you sort of interpret it? It's shot off at an angle of 30 degrees. Yeah? Okay. If its flight is interrupted by a vertical wall 12 meters away, at what height does it hit the wall? Missiles fire from a slingshot 30 meters per second. It's fired at an angle of 30 degrees horizontal. If its flight is interrupted by a vertical wall 12 meters away. Okay. So let's kind of call this the release point here. And so 12 meters away, there is a vertical wall. That is 12 meters away. Okay. At what height does it hit the wall? Ah, okay. So it's kind of asking that question, right? What is the height there? Yeah. Okay, well, this here is kind of what they're asking about. What they're pointing to is a 1 spot right here and a 2 spot right here, right? Okay, so I'm actually gonna, I want to make this a thicker green. Right? Okay. So there's a 1 spot and there's a 2 spot. Right? Okay. So let's just do this. Do our little inventory. Okay? So in the X and in the Y. Yeah? The Vx, it's going to be constant the whole time because there is no acceleration in the horizontal direction. Right? This is a pebble that's flung in a slingshot and it's just flying through the air. Yeah? So there's no, you know, we're neglecting air resistance here, but basically there's no way for that thing to sort of like change its horizontal velocity, but there is a way for it to change its vertical velocity. So let's say that there's a gravitational acceleration, and let's make negative. So up is positive and to the right is positive. That's going to be my choice. Okay, and then delta D and delta T. So we can kind of, you know, we could ask this question of X, V1X, V2X, AX, delta DX, and delta TX. But actually, 2 of these are kind of silly to ask, okay? Because this is 0. Acceleration in the horizontal is 0. That's important, okay? So because AX is 0, that means that these 2 are really just going to look like Vx. Okay, and sorry, it's not 0, but it's just some constant V. It's not V1 and V2 because they're the same. So why would we call them something different? Okay. Okay, so then it's just Vx. Yeah. And AX is 0. Okay. And delta D in the X we know is 12 meters. Right? But we don't know how long it takes. So they're asking at what height, so that's the delta D in the vertical. So let me just represent that a little differently. Let me call that delta H. Okay? We don't know what the delta H is. Right? And we're assuming that it's fired from the ground. Okay? So let's actually bring this whole thing. Let's bring that down here, and then just say that that distance there is 12 meters. Right? Okay. Okay. So that distance there is 12 meters, and it's asking kind of like where does it land? Where does it land? Right? So it's asking what is the height? Okay. So I've kind of drawn this poorly, but that's my horizontal there, so that's my wall. So let's put the wall to the ground there. Okay. Okay. There we go. Okay, so we don't know delta H, but we can try to find it. We don't know delta T, so that means we must know something about these two. Do we? I don't know if we do. So V1, we do know Vx. Yeah, I think we do know V1x. Okay, so V1 in the one case is a diagonal, which means we can break this down into a V1x and a V1y. Right? And that V1x is actually just Vx. So that's Vx. Okay, so Vx is, and this is 30 degrees, and this is 30 meters per second. So Vx is 30 cos 30 degrees, and Vy is 30 times the sine of 30. So that should just be 15. And that is 25 point, let's just say 26. Okay. And so we're good here. So this is 15 is our V, oh no, sorry. Vx is 26 meters per second, which means we now can calculate our delta t. It comes from this equation, which you might not be able to see because of me body. So okay, and this program is getting a little full, so let's just rearrange here, and we get delta d over Vx. So we get 12 meters divided by 26 meters per second. And so we get 0.46 seconds. And now we can answer this question of the delta H, okay? Because we have our V1y, and we have A, and we have delta T. So let's just solve that. So let's maybe make this a little smaller now that we've digested it a little bit. Okay, this here, let's make that a tiny bit bigger. And this, and then this is solving. Delta T is equal to that. And so 0.46 seconds, 0.46 seconds. And V1y is 15 meters per second, and that is from this. Okay. Okay, so then here we can solve these with a little bit of delta H is equal to V1 delta T plus 1/2 A delta T squared. And we can solve from there. Keep going, let's plug them in. So delta H, we don't know what that is. We're solving for that, so that's good. 15, I'm glad we have delta T here, so we don't get anything squared. Plus 1/2 negative 9.81 times delta T squared, so that's 0.46 squared. We're just plugging these things in. 0.46. So I'm just going to hold this in my page here instead of my calculator. So then it's minus 1.0368 minus, and so we get 5.86 meters. That looks like that's our delta H. And that asks at what height does it hit the wall? So it's 5.6 meters up the wall. Okay. Boom. Okay. Not bad. Okay. Love it. All right, let's keep cruising. Actually, let's take a little break. Okay, just want to check in with the lady love, and then we'll be back. Maybe what we'll do is we'll watch a little video in that time. Okay. See what we got. Um. Wait a second here. So, all right, let's do it. 7 as well. Do you know? Oh, sorry, yeah. Okay. Where am I looking? Okay. Still some of those later questions, right? Any of the earlier ones that you were like, wait, I thought I got this, and yeah. Okay. Okay. So just grab scene. If you want to maybe just even tell me the ones that you did get wrong in that sort of earlier group, I can scan around.
Okay, I'll be back.
Yeah. 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 Okay. So a lot of that towards the end, right? Okay. And even when we get into the 30 range, it's like a little more difficult, right? Okay. So let's just grab a few of those. Start there. So I'm not sharing yet. There we go. Okay. So what's your methodology here? Remember, what does the absolute value do? Yeah. It kind of makes whatever's inside positive. Okay. So first, let's solve what's inside. What is inside? Oh, okay, wait. The absolute value doesn't meddle with the signs, like it's a sort of a, it's a, it's a function, right? Functions take one thing and give you another, right? So the one thing that they're taking They don't, it doesn't kind of like affect the other. What you would be doing would be distributing that in some way to affect it only on the -6 and the 7. First, we have to do that. Remember, there's a bracket here. This also counts as a bracket. And so we can only give it one thing. First, we have to solve that one thing there, that red bracket, and then we can take or ignore the sign of that thing, right? So it will -42 plus 32. Good. Yeah, wait, -10 or +10? Yeah, right. The answer inside is -10, but then we take the absolute value of it, right? So that you will only take the absolute value, like you can't really distribute the absolute value. Most, squareds, like you're sort of used to, this is the most dangerous one, right? This distribution here, because then you're tempted to do it here, right? Which you can't do, right? But you've maybe accidentally done that one, right? But you can distribute like some other things too, right? Like even a constant out front, right? This you can distribute, right? Absolute value, like those are all functions. Absolute value, you will never be able to distribute. So you always have to sort of like just give it the one thing, one number that's there, and you have to sort of like work from that point, if that makes sense also. Sometimes you'll also have a variable in there, right? So we'll be able to say when the inside is negative or when the inside is positive, depending on the x value, right? Okay, but yeah, like that's sort of like, I think, more helpful for some more complex ones, right? Okay, so let's look at this one. So factors of polynomials. This is your advanced function stuff, right? Didn't you start with polynomials? This is a cubic, right? But it's not even that hard of a cubic because it's one that we could have given you grade 10. So you got this, obviously x out front, and what was the other one? Wait a second. 2 and 2x minus 3. Sorry, you lost me. Yeah. Um, how did you factor this? Yeah. Ah, sorry, I didn't hear that one. 2x minus 3. Right? All right? No, plus. All right? You said you got 2x minus 3 out of it? What was the other factor you got? You got x minus 3 and? I heard like a double bracket there. Something like that. Can you show me? Can you just show me? That's okay. Oh, okay. You're saying sort of along the way. Okay. But then eventually you get this, right? Sorry. I thought you were giving me this one. Sorry. Okay. So, yeah, good. That works out. X is not a factor. Didn't you start with that? Right? Remember, what you have left is a quadratic. You started with a cubic. You got to keep it a cubic. Right? So you got to this, and then that you turned into this, right? But that X was still out front the whole time, right? So any of the others that you got? No. So just F, right? Okay, sorry. Okay, so let's jump to this one. Okay, so we get some sort of extra pay, 1.5. How much per week? Which earns 47. Okay, so this is kind of like a piecewise type function, right? For everything under this value, do this, and for everything over this value, do that, right? Okay, so how do you do this? Y 10 times 4? Yeah, 10 times 40, so 400 times the pay, right? Yeah. Oh, okay, okay. What'd you get? Okay, yeah, yeah. So something's up, right? Like if I was going to get $400, like that's part of that zooming in, zooming out. Like if you do have a second, sounds like your speed is pretty good here. The zoom out is like, does this make sense? What's the best thing I could do? If I got paid $400 for 40 hours and you gave me $410 for 47 hours, right? Like that right there is a signifier, right? So that's you were in the zone and you just kind of moved on, right? But zooming out, you can say something's wrong, right? And catch that, right? And that's sort of sometimes the difference. That's like the subtlety between like 85 and 95%, right? Like catching those little silly mistakes, really, right? Because it's not like you didn't know to do that. Okay. Can you give me a couple others here? Okay. 3. Yeah. Okay, so this one is about this. Did you have any trouble with any of the others, 35 to 38? Was it just the 38th one there? Okay. Um, okay. So then let's go from there. So we'll start with 39 here. Oh, okay. Okay, so like we take this for granted, right? This should really have a 2 out front because it undoes this, right? So what do you think this undoes? Yeah. So anytime we put a number there, it kind of indicates, and remember that these are actually, when you rewrite them, that's actually to the power of 1/2 because it undoes it, right? When we multiply them, we get, I mean, if this was an x, right? We get the something to the power of 1, right? So here, to get to something to the power of 1, this would be 1 over 3, right? So, same story. Whatever this number is really the, denominator of this fraction. It's a 1 over. Okay? Okay, so then how did you sort of start to solve here? Oh, we could do it faster. Okay, so, right, like 10, let's take 10 away from both sides. Right, we can just solve. Start to solve. So we have 3. How do we undo a cubed rooting? We yeah. But wait, how do we undo it? Which is what? You cube it, right? Remember, they are designed to undo each other, right? So we're going to cube this thing, which means we also have to cube this thing. And then we just get plain old 3x minus 9 is equal to 3 cubed, 27. Add 9 to both sides, and we can maybe stop here, right? We get 36, and now x is, yeah, right. Okay. So, um, yeah, whenever you have, like, knowing that this is a solvable equation is really the sort of like big step here. How do you know? How do you know equations are solvable? So you should be able to tell me when this one, or even let's just do it simply, to involve two variables. Yeah, right? But if I tell you that this, well, this I haven't hidden the number of basketballs I tell you if I tell you the number of basketballs I have minus 2 is 5, but I haven't told you the number of basketballs I have, right? Well, you can just solve for that. So this one is like, no, it's impossible. I can always trick you, right? So same thing. Here, one equation, one unknown. It's solvable. Let's just attack it. Yeah. Like there will never be really anything that you can't undo unless it's like a trig function. It will be really kind of tough or tricky, really. You just probably are going to use one of your nice triangles, right? One of your 3, 4, 5 triangles or one of that. But otherwise, one equation, one unknown, it's just undoing all my old friends. Multiply by 2, division, square root, all that stuff. Okay, so suppose ABCD is a standard XY coordinate plane such that BC is on the x-axis. The midpoint of BC is the origin. Okay, so let's kind of like draw this thing that they're describing here. Like that, right? Okay. A has positive coordinates. Yeah, sure. Um, what is that number there? And one coordinate unit is equal to 1 meter. So like one of these cubes, I'm assuming, or one of these squares. So what is the coordinates of D? Wait, what do you mean by 90 degrees? Oh yeah, sorry. Was this the one that you struggled with? Or you got wrong? Or, okay, so let's just take a second here. Point M starts at A and is rotated counterclockwise about P, a total of 450. Okay, so I'm going to ignore the first 360 of that because that's just going to return me to where I am, right? So then that's an extra 90, and it's counterclockwise, so it's this way, right? So I should go here, right? Like my shape should rotate by 90, and my shape I think is equilateral, kind of, right? Okay. M is at the same location as which of the following points? D, right? Yeah. Okay. So then 38. So I drew the sort of like coordinate system that they describe in the first sentence. And it says A has positive coordinates and one coordinate unit is equal to 1 meter. Is that going to be helpful here? No. That's a distraction, right? That's a smoke screen. What are the coordinates of D? There's no meters featured in any of the answers or anything. It doesn't matter. So what are the coordinates of D? Okay. Well, I drew the thing there, right? So you should be able to sort of tell me what D's coordinates are. Yeah, J. Yeah. Okay. This is actually one I've seen on multiple tests before. Not likely to like see it again, like generally when you see kind of like one question that has the, for the next 4 questions, this is the thing that matters. You won't see one exactly like that again, but I have seen 2 that are similar to this. Okay. I think it was like P was like somewhere, P was like on the left or something, but it was very similar. Okay. Um, so there was another one here, 33. Circumference of a third circle is 20 centimeters. What is the length centimeters of the radius of the circle? Oh, okay. So, what'd you do? Okay, what's the circumference of a circle? Good. Oh, did you write it down? Oh, okay. So that means we got to do that check, right? Of what we talked about, right? Is the exponent on the formula matching what I'm looking for, right? So that means that, we all have our common mistakes. Like for me, you know, um, inequalities, right? Like I still have to picture, like the alligator eating the bigger number, right? Like I can do like, sort of algebra with these inequalities, but I still have to think about it in a silly way. But because I know I kind of am bad at it, I don't really make the mistake because I have that sort of like adjustment, right? So that's like, it's on my radar. That little that little equation thing, because I think that's sort of the second time maybe where we've had the circumference thing, right? Or we've kind of like, played with it. So, okay, we just have to add a little check there, right? And that's the thing, the R value, right? Or the exponent on it. Okay, so then obviously I don't think this is that challenging, right? I don't think we need to do this. Well, yeah, yeah. Let's do it. Yeah. Oh, okay. Okay. So, cos of L is 7/16. What is the sign? Okay, so this is close to the one that I think we've seen before, right? Where they don't ask us exactly ever about the angle. They ask us about the trig of an angle, right? So we can get away with just using the ratios. This may not be the true side lengths, but I'm going to use these values as if they are cos, which is ka, so this would be adjacent to L, 7, and then hypotenuse 16, right? Which means now I can kind of solve for this, right? Which I'm imagining is 207. I don't even have to do the math on it. That's another beautiful thing, right? Um, I mean, I might get burned by that, but like this is pretty. I'm pretty safe in that, right? Like I don't think this matches up to anything nice, right? Because 7 is prime, 9 is prime. Yeah. What is the sign of n? Okay, so now. Okay, so did you draw on it? Ooh, yeah. Oh, okay. Ooh, okay. I see. So you did 7 over square root of 2 of 7. Yeah, yeah. And remember, the cos of my angle, like if we are the two opposite angles in a right angle triangle, the two that matter, obviously not the 90, the cos of my angle is the sine of your angle. Like look, the answer is 7 over 16, right? So the cos of my angle from my side is my adjacent, which is your opposite, right? So the cos of my angle is a sine of your, and obviously your cos is my sine, right? So that's something you could use here too, right? Another even faster way to do this. Okay, but drawing that, like, not even hard, right? You know, it doesn't even have to be a nice triangle. You can give me one of these, right? And it's like worth it to do it on the page just to see it. Okay. Okay. Let's keep going. What else we got? 50 or anything in the 40s here? Okay. Okay. And so what was the sort of like mental fatigue level like going into it, but also like getting towards this level of the test? Okay. 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 No, I mean, and it's like it's worthwhile sort of data to have regardless, right? Like, and it's good. It's like honorable that you're putting in time regardless, right? So, and that will like pay off. So, um, there's no reason to like be upset with that or anything, right? Okay. So 44. Lynn has. Okay, sure. Yeah, I know. And that's what they're designed to do. They're designed to be wordy. The math is like usually addition or something, but designed to be wordy. Notices that there are 5 more dimes than quarters, 1 more nickel than quarters, 25 more pennies than quarters. Okay, so I'm hearing an x equals quarters, x equals number of quarters. How many pennies? Okay, so all we can really, like ignore the first part and just say this, right? But then she has this much, right? Okay, so let's just kind of say start with x is the number of quarters, right? And it's probably been a while since you've done one of these questions, so you'll recognize it, right? But the count versus the value are going to be our two equations, right? So we know that the total value is 3.67, right? So let's kind of call, for a short time here, let's call x, let's call y the number of pennies, let's call z the number of dimes, and let's call w the number of nickels, okay? And really, they talk to us all in terms of x, right? So let's kind of like solve for the equation of each of these. So how do we find the number of pennies? If I have the number of quarters, let's say I have x. Yeah, good. What else? Okay, so now the total value is going to come from each coin's value, right? Wait, does she have certain, no, she doesn't have, we're not told how many she has. So let's just kind of like use the total value here. It's going to come from what? Good. But remember, this is the number of each of those. So what do I have to do with the value for the number of dimes? Yeah, but each one of them is different, right? So dimes will be this, and then that's by dimes, so that's x plus 5. And then to that, we add, you do the next one. Yes. X plus 25. Yeah, good, right? Like we need to do that, right? Good. And then anything else? Was that included in the value of the 365? 367? Yeah, it is. So we should add it. And what's its value out front? And what's its number? Just x. Just x. All right. So now we have a big old nasty equation for x, and we can just solve. Right? So, yeah, this is sort of like the value, and like you can do this by also using this on a multiplier to this, right? And taking it away from our total, because you'll end up with 0. That, and then a 50 cents, right, of dime. So let's take that away, right? And then, right, you with me? So you can kind of do it that way too, and you can do it faster that way. But generally, this is the sort of system, and you'll see a few like this. Okay. Okay. So what did you get here? Yeah. 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 So I would look to the I would look to probably, yeah, I guess it's tough, right? Because quarters could jump in there too. But I would look to the nickels. One more nickel than quarters. So yeah, I guess it kind of all jumps back to how many quarters you ask. You can't really do any trickery with like that. Besides, like there has to be at least 2 pennies somewhere, right? So 7, 12, 32 are the only valuable ones, right? Okay. Consider the transformation of the standard maps each point to the x, sure, for a certain positive constant. So are you understanding what they're describing that first sentence with lots of words, but they're basically saying they're going to stretch it. Right? In particular, this transformation maps this to this. Okay, so they've kind of given us a, okay, so they gave me a 3 comma 9. We have to find the k value, but it's on to 3 comma 9. It becomes what? Oh, sorry, 1 and 3. So it's 1/3. So k is 1/3. So then apply that to this, right? Yeah. Oh, yeah, yeah, right. Yeah, but it's a K, right? It's a multiplier. Yep. Okay. So yeah, I mean, this sounds like one of those ones where it's like you got to get burned before you know that it's, to be aware of it, and you're going to remember it from your scar, right? You're going to recognize this type of question if you see it again. I don't think you're going to get this one wrong again. Okay, and that's what we're doing. Part of this is just exposure. So matrix multiplication is kind of like the dot product of two matrices instead of the dot product of two vectors. The dot product is for vectors, but matrix multiplication is for matrices, but it's the matrix version of it. Okay, so this is the kind of like general idea here for any sort of 2v2, and if they don't exist, like if it's just E and G on the right one for us, right? Then the F and H terms don't exist, so that's those ones there. So it's just going to be one of these vertical ones. So you'll only ever get, I think, 2v2 multiplication, okay? There is matrix multiplication that doesn't work. It doesn't make sense. That's not allowed. Where the amount that I'm lining up with the vertical amount doesn't work. So say, for example, I try to do this and multiply it by this. I can't do it because it's asking me to take these three things and line them up like this, but what does this line up with? Right? So that's the problem. You can have matrix multiplication that isn't like possible or allowed. Okay. Okay. So that's sometimes the answer. If the question seems really hard, that might be the answer too. Okay. Okay, so 52, 54, you said as well. Just grab, okay. And something else that's worthwhile that we have the advantage of is to look at where you are getting because I'm seeing a lot of these like in the standard plane type questions, right? Which might mean some focusing on those types of questions, which means going to the test, seeing which types of questions those are, and just doing those questions, and then moving on to the next test and doing it, right? And then come back to that test like 2 weeks later, and you can probably do most of those questions again and forget about it. Okay, what are the real values of m, if any, such that any line through the point, whatever, will be vertical when graphed? Okay, so it needs to be a vertical line. Okay, what is true of vertical lines? So keep the x constant and tell me what m can be. Why can't it be 7? Mmm. Okay. Oh, I like that. So, yeah, I'm with you on that. So is the answer J? Yeah, right. And it would need to be a line. Uh, no, no, that's it. Okay. So that kind of came to you where, like, did that just was a little too confusing or too wordy at the time? What did you feel in the moment? Okay. Okay. Yeah, because it was like you were confident in it just now, right? Okay. Yeah. Sometimes that is like, the sort of mental fatigue level of these questions as well. And it might be worth it even to kind of like take a peek at some of these too, like at the start and try some of them and then kind of like get back warmed up, come back to them or something like that, right? Might be worth evaluating your strategy. Okay, so sure. Which of the following is not true? Okay. 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 Yeah, so now with the time to evaluate it, tell me, like, do you know what the true answer is? Yeah. Okay. So let's kind of like provide proof then. This is one of those ones where we can at least like think through it, provide proof for all the others. So why is F true? Hmm. So what I'm saying is f of x doesn't change when I take the absolute value of it, right? Do you agree? Why doesn't it change when I take the absolute value of it? Some numbers do change. Why doesn't f of x fall in that category? What types of numbers change when you take the absolute value of them? Sometimes you take the absolute value, doesn't do anything. What type of numbers am I talking about? Positive numbers, right? Like absolute value, all it cares about is this thing positive or not? If it's positive, it just leaves it alone. So the absolute value of a positive is just the same thing, right? The absolute value of a negative is when it gets changed. So if I'm telling you that f of x doesn't ever get changed when I take the absolute value of it, I'm in a way I'm telling you it's always unchanged by the absolute value, which means it's always positive. Is that true? That it's always positive? The value of f of x? Why? Why? More easier than that. Look at your graph. It's above the x-axis. It's above the x-axis. All of its values are positive. Is that true of g? No. Sometimes when I take the absolute value of g, it doesn't do anything on the right side there. But when I take the absolute value of the left side there, it changes, right? Okay, so then f of 3, sure, yeah, they're equal to each other. That's where they touch, right? F of 3.5 is equal to 3.5. Okay, that's kind of hard to tell, but I guess those are two numbers that you would plug in and try, right? And then f of g of 1 is equal to 6. What is this? F of g of 1 is equal to 6 is the claim. Okay. Yeah. When I plug in 1 into g, you mean? Okay, so then that's really the same as f as 1 if g of 1 is 1. And is f of 1 equal to 6? Yeah, so that's good. Right. Okay, yeah, so you've seen this kind of notation before. Just wanted to kind of like check that. Okay, it's not so scary, right? You just kind of like do it first, then plug it in. Okay. Uh, so, so you said some of the later ones, 58, 59, 60. Okay, so I think we've looked at one similar to this before, right? With the parallelograms. Is that right? Okay. Okay, so now you have time. Let's kind of like, without time pressure and without, being too stressed about it, let's see if we can reevaluate. So I'll give you a second, and even if you do know the answer, let's sort of like make sure we know how we're getting there. Okay? I'll just give you a minute, see if you can feel comfortable getting there yourself. Okay. So um, let's sort of start by sort of saying this midpoint stuff. Are you comfortable that we're going to get kind of like the same, the same kind of trapezoid, like in terms of angle, but just a little bit longer side there, right? Is that fair? Okay. So where this one's 12 and this one's 25, right? And then there's even a bigger one than this. Let's just maybe do this. There's an even bigger one that is kind of like twice in some way. Okay. So this is actually an easier one first, an easier stepping stone before getting to here. Okay. So how much grew on each side here from 12 to 25? Like total of each side. We don't know which one got which, but 13. Okay. So then going twice the distance, we should gain, yeah, because we're going to gain another one of those. Comfortable with that? Okay. So now we know that the total down here is what? Another 13 on top of this, right? So 38. And now we just have to find a number right in between 25 and 38. Yeah. Yeah. So a lot of this is like smoke and mirrors, right? So and remember, like designed to be less than a minute. And then that includes like a 15-second, let me check if this is right. Let me make sense of this. Let me zoom out. No, not 20 minutes. No, no, no. Like the most I've ever like seen somebody consistently finish is like 3 to 4 minutes, which is like pretty fast. Pretty fast. I know, eh? Yeah, especially when you're like, wow, could have used this like extra half hour I just like it just destroyed this test on. Yeah, it's true. And it really only comes into account on the math test, like and science too, but it doesn't seem like for you, which is good, but yeah. And like I said, like the math section, the math is a problem or the time is a problem. You do get a lot and you borrow a lot from those first 45 to use on these ones, right? Okay. So it's randomly selected from those, so we got a 1 in 5 kind of chance here. That B will be randomly selected from, okay, 1 in 4. That A times B is bigger than 0. Has to be bigger than 0. Okay, so talk to me. Good? No, 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 yeah, it's not 7. It's not, that's not how we do it. So, like, what multiplies to become bigger than 0 between two numbers? The numbers, can they be both positive? Can one be positive, one be negative? if one's gonna be negative, they both be negative, right? Okay, so either it's -2 and it's 3 possibilities with the other one, right? Or it's -1 and it's 3 possibilities with the other one, right? So are you comfortable with kind of like that, where those are coming from? -3, -2, -1, right? So that's a total of 6, right? Okay. And then, so those are the negative ones. What about where, uh, where it's positive? Yeah, good. Yeah, I really should do a tree like this, right? Like another option might be, I might look to do a complement type question where it's sort of like a 1 minus, right? Like if I say, what's the probability that everything, you know, that nobody has duplicates of X, then I'm going to look at the one that doesn't have any duplicates, right? And do 100% minus that value. And I'm going to figure out all the ones that don't have duplicates, right? Or do have duplicates. Sorry, that's a backwards thing. The complement stuff, if you get to the data management, kind of makes sense. I explained that poorly, but this is kind of called a tree. So the options aren't too crazy, but yeah. And then the total is what? Why? Yeah, 5 options, 4 options, right? Okay. Oh, word salad. Distinct points A, B, C are collinear. What does that mean? They're on this. Yeah, they're collinear. Yeah. And B is between A and C. Okay. For D to be between A and C. Okay, so now that you know they're on the same line, do you want to try this one? If B is between A and C, then A plus B. So, yeah, there's no requirement for those things to be equal, just for sums to be true, to be sort of like equal certain things, right? So that could be 7, 9 and 1, 7 and 3. They don't have to be equal to each other, right? Okay. Uh, B is between D and C. Okay. Well, let's kind of leave that for a second. Let's say why 4 isn't true. D is between B and C. So look at the statement that they give you, right? Look at the sort of steps that they take. They say start at A and then go to D, but then right from D go to B, and then right from B go to C. So this is AD, this is DB, this is BC, right? And so we actually have gone A to C. So where was D and B in that arrangement? Yeah, right. So that was the statement that they gave us. Okay. Um, Okay. So yeah, I think like maybe I can here. I'm gonna send you a couple extra because you have now I think one extra, right?
When I say mango, you say buble. Mango! New mango buble. Here for a short time, but a great time.
Hey guys, I'm really excited about this because this is the start of everything you need to know for A-level maths. This is the pure section, and the lovely Miss Phoebe is going to be taking you through each skill one at a time. For every single skill in here, there is a much longer video going through each skill at 3 different levels, lots and lots of questions. So if there is one bit that you're not too sure about, go and watch the longer video where it's explained and lots of examples are worked through to help you ensure that you can do each of these skills. Over on my website there are thousands of multiple choice questions just waiting to help you revise and make sure that you've got the confidence in these skills so that you can go into the exam.
There we go. There we go. So and t to the 3 plus, well, 2 doesn't have a derivative, so it's just that, or its derivative is 0. Okay? So, okay. Not bad. We're getting there. Right? Okay. 6. All right, finally, we get some new names in here. Some fresh air. 1 over 2. Oh, that should have been an f of t as well. Ugh, how embarrassing. Is it more embarrassing than I just did that? Okay, boom. F of t is 1/4 3t to the 6 minus 3t to the 4 plus 1. So I'm just going to go right into it. We're just going to get 3t to the 5 minus 12t to the 3, and that's it. Bada boom, bada bing, maybe. It's getting too easy. Alright, that's 6 done for you. For your very eyes. Alright, let's do it. 7. Is y is equal to x to the negative 2 over 5. Okay, let's do it. So the rule is the same, right? Y prime is going to be negative 2 over 5 x. Now we have to subtract 1 from that, right? Is the rule. When we take the derivative, we take the constant exponent, we subtract 1. So that's actually going to be minus 7 over 5 now. But there it is. Same rule, right? Boom. Dunzo. Okay. 8. Come on, let's get some pretty 8s up in here. Better. Okay. Y is equal to 5e to the x plus 3. Okay, so this is our natural number e. This is the first time we've seen x in the exponent. Okay, so what we get, and we could prove this using, of course, we could prove all of these using limit definitions, but all of these sort of turn into just rules that we memorize. The derivative of e to the x is actually, with respect to x, is actually just e to the x. Okay, but there's a hidden thing happening here, which is that there could be a function in that exponent, and the function would still be there, but then we would also have to multiply, because of chain rule, by the derivative of f of x, or, you know, d f of x dx, right? So if there's a function in the exponent, or if it's not just plain old x, because the derivative of x is 1, so that's convenient. But if it's not, then we have to take the derivative of that exponent. Okay. So that is our e to the f function. So here it really just becomes 5e to the x. And the 3 is like any other term that we would do over here. Right? It doesn't show up. So, okay. Let's keep it going. All right. So, ooh, B of R. For some reason, I picture this as, you know, Germanic dysfunction. Ooh, okay. So pi is a constant. It's just instead of a 4, using the symbol 4 to represent a constant number, we use the symbol pi to represent a constant number, right? It's a little bit of a uglier number, but that's just your subjective view of things. So 4 pi over 3 is another way to write that, is just the constant out front. That gets multiplied by 3, which turns out into just 4 pi, because the 3's cancel, right? And then r is the variable here. So that thing, the rule is, gets reduced by 1, right? Okay. Let's keep it going. That's 9, 10. I think after this one, get a little drink of water, have a little tangerine. But let's do it. So r of t, okay. I don't know what I picture for this function. Maybe an avid reader, I think. Am I just like that simple? Am I a simpleton? That it's just the letter that it starts with? Okay. So r prime of t is the child, right? Disappointingly so, not so much of a reader. Okay, but they do listen to audiobooks. So, okay, so 5 times -3, right? Over 5, we'll just cancel the 5, so we'll just get -3, and then the t, so that, sorry, that should be a factor out front, that has to be subtracted by 1, so we just get -8 over 5, right? Boom. Okay. Let's do it. 11. Oh wait, did I say I was gonna take a little drink of water? Okay, let me mute, just get a drink of water here. Okay. Before we start 11 here, I'm just gonna peel the tangerine. Will not get the ASMR unless you want it. It's called for in the chat. All right. Tangerine is peeled. Slices at the ready. My hands are all wet. Okay, let's do it. Another grind. Okay, we'll take a proper break at 20. Where are we here? Let's do it. Y of t. Okay, this is starting to get repetitive, so hopefully things get a little bit more complex here. Oh wait, you know what? That's it for this one. Let's do some of these. Okay, so this is where our chain rule gets introduced. So, let's do. Ooh, we didn't really see any. See any quotients, right? So let's maybe do that first. So let's do t is equal to 2t over 4 plus t squared. Okay, so this is a quotient. Now what I would recommend is actually treating this like a product, okay? So we have the division of two functions, so we're going to have to do something with the fact that there's a division there and do the derivative of that division somehow. And then we'll also have the functions on the inside, because you'll probably be able to tell the derivative of the top is 2, the derivative of the bottom is 2t, but you don't just take the derivative of the top and divide it by the derivative of the bottom, right? It doesn't work out that way. So let's actually do 2t. Let's sort of say that this same thing, f of t, is equal to 2t times 4 plus t power of 2 times -1. Okay. Now I'm going to do chain rule. Now this is kind of like the outside, right? This is the function on the outside. And what would be the derivative of that? Well, it would be bring the -1 out front, and this would go down to -2, right? So let's kind of do that on the outside and then take the derivative of the inside. So this is the chain rule, that we can kind of get away with this outside-inside trickery. Yeah? Okay, so let's keep it going. So, and product rule, you know, we could show this, that this is maybe something that belongs somewhere else, not necessarily in the challenge, but, you know, when we have u times v, the derivative of that, we will get u prime times v plus v prime times u. Okay, so you kind of take the derivative of each and keep the other original, right? And add them together. Okay, so let's do that. So what that means is this, let's not use blue there. This here is our first thing. This here is our second thing, right? So the derivative of the first thing, remember it's u prime v plus v prime u. right? If this is u times v. So u prime, what is u prime? It's just 2 times v. So we have to keep that original, that whole thing. And then plus, okay, not bad, we're already halfway there. Plus v prime. Now that's the ugly one, but do we agree that there's going to be at least a 2t there? Now the derivative of this is the derivative of the outside times the derivative of the inside. So we get a -1 times a 4 plus t squared minus 2. That's the derivative of the outside. Now the derivative of the inside is 2t, right? And you'll notice that that thing we can kind of factor out of both of them, right? So if we wanted to sort of simplify this, we would factor everything. We could take a 2 out as well. You'll notice we can kind of like bring some 2t's times 2t's together. This actually isn't plus because there's a -1 in there. So let's make it kind of like a little more fair representation. Let's say 2 over 4 plus t squared. That's what this term is, this whole term. And in fact, that is found in this one as well. So let's just say 1 plus, and what happens when I factor it out of this one? That one of those goes away and the 2 goes away, right? So what are we left with? We're left with minus t squared up top. I think actually 2t squared because that 2 sticks around even though we got rid of the other one. So minus 2t squared over 4 plus squared. And we could maybe keep it there. That's pretty nice, right? Okay. So that one is, it's a little sloppier, it's a little nastier, but that's just the way it goes. And we were kind of showing product rule in a quotient, right? So, no, it's kind of the way it goes. Okay. So let's do it. Let's put that in tome here. Um, Is this maybe the best way to do this? Let's maybe do this. Okay, a little bit of a crazy start to whatever the song is. Let's do some rearranging here. All right. Actually, okay. So let's do it. 12, right? So what was 12? Okay, so 12 is v of x is equal to 2x cubed plus 3 x to the 4 minus 2x. Okay. So let's do this as a product rule, right? So let's say v prime of x. This is going to be our first and our second, right? And then we'll do derivative of the first times the second plus derivative of the second times the first, right? So let's, and then we can even kind of do this, right? Let's do that. So that plus that, but in the first circumstance, we're going to take, so we're going to sort of keep that original, but we're going to take the derivative of the first one. So what's the derivative of that? It's really just 6x squared, right? And then in this one, we're going to keep the first one, and we're going to take the derivative of the second one. So what's the derivative of that? It should just be 4x to the 3 minus 2, right? And now that can all be kind of simplified. So let's just kind of follow through on that. we can say 6x to the 6 minus 12x to the 3 plus, and now this one will have to expand. Can we do anything to simplify? I don't think so, right? So let's just kind of do it. So, ooh, what do we get? Okay, so we're foiling, right? We can't even bring any 2's or anything out. Okay, so 8x to the 6 plus 12x to the 3 minus 4x to the 3 minus 6, right? Okay, so let's kind of bring all the x to the 6's together, right? So that's 14x to the 6, and then all the x to the 3's together, so the plus 12, the minus 12, so we're just left with the minus 4x to the 3, and then we have minus 6. So we can kind of take a 2 out, but why bother? That's our derivative, baby. Not bad. Okay. Pretty tough one. You're getting tough. You're getting tough. Tough on crime. 13. What is 13? 13 here is u to the minus 2 plus u to the minus 3. Uh-oh. Times u to the 3 minus 2u to the 2. Okay, so it doesn't matter that it's now a different variable by a different name. We're going to kind of treat it the same way. And honestly, I might factor out some things first, right? Because I could probably get an u to the 2 out of both of those, and I could get a u to the 2 out of both of those, right? And one of them would be -2, one of them +2, so maybe they cancel, right? So I'm actually going to do some rearranging first. I'm going to say u to the -2, factor that out, I get 1 plus, now let's be careful about this, that divided by u to the -2 is u to the -1, right? So then u to the -1, and out front of this one, we can get u to the 2, right? And we get u minus 2, right? So what a surprise, those u to the 2, u to the -2, they cancel. This gets a lot simpler. We still kind of have to do this, but let's even maybe just turn this into a quadratic, really fully learn the lesson here, because something's going to be nice, right? So u times u to the -1 is just 1. This is, we're doing FOIL. That's all we're doing. So plus 1u minus 2u to the -1, and then minus 2, right? So we get okay. There we are. We're back. And I'll just jump in the Discord channel. If anyone needs in, you can jump in. Throw this here. And maybe we'll get back to it. So let me just get a little bit of schmooze. A little bit of schmusic. Schmuzia. A little bit of schmusic. Let's just say this. Okay. What kind of music are we in the mood for here? Let me just get this. This going.
If you want to achieve better results, make a great impression, and save time at work, you should get Grammarly.
With Grammarly, it's like I have my own personal editor on every email or message or essay that I write.
Cute. All right, I think we're good here. Okay, let's get back to it. So, Samuel, I'm gonna grab your question for now. What do we got? This file actually looks like it's getting a little bit too big. So just give me a second here. I'm just going to open a new file. Run a third already today. Tab 8C. Alright. And put this there. And we'll get a couple of these. Okay. That. Oh, hey, Ambrosia. Up here. Okay, and then we can do a little bit of statties. Alright. Alright. So let's do it. Alright. Samuel, let me know when you're ready. Alright. Got your question there ready for you, Samuel. Alright. In the meantime. Okay, excuse me. Just need a little coffee. Hey, Samuel's back. Alright. Let's get to it. Put these to the side for now. Samuel, when you get here, you're number one, alright? Let's go. Okay. So a pendulum swings, right? This is something that you can do for sure, right? Just move something kind of back and forth between its two extremes, right? On either side, yeah? And if I catch it at one spot, let's say I snap a picture of it here, okay? That's what it's done. And this is the point P, right? But I've snapped a picture of this box. Yeah? It asks, what is the instantaneous velocity? So velocity means what? It means speed, right? Essentially, with a direction, but it basically means speed. So what is that box's movement? When I took that picture, where was it going? Forget about where it came from. Forget about where it's going. But at that moment, where was it going? If it didn't have the sort of future that it did to curve upward, it would have continued on that kind of exact same, so this is that tangent velocity. It would have continued. It's like spinning something on a string and then letting go. It continues on the direction that it was going, right? Whenever you let it go, okay? So that is the instantaneous velocity. Instantaneous means in an instant, right? At that moment, at that one instant, what is its velocity? It's the tangent velocity. And so, what is it? You should be able to tell me what the answer is. Gotta have some confidence here. When we were talking earlier, Samuel, you were asking me in a very not confident voice, is this the answer? So is it this? And you didn't know, but it was the answer, right? So that means you owe me a little more confidence, right? Usually when you ask something with not confidence and you say, is it this? Usually the answer is wrong because you weren't confident, right? You got this. So the question is, which arrow best represents the speed at that moment, right? At that moment, right? It says at P. Not here, not here. Forget about A and B. But if we were to sort of like stop it at that moment and forget about the rope and record all these stats about it, we could say it's mass, we could say it's maybe it's acceleration, we could say, maybe it's velocity, excuse me, right? Maybe it's color, right? Things like this. Well, the velocity would be one thing and it wouldn't have anything to do with moving in this circle, right? So at that moment, it's just an object moving in space in the direction that it's going. Okay. I hope that helps. What is? Oh, okay, sorry. Okay. All right. Okay, hit me with another one. We got chemistry homework. Talk to me, Samuel. Put it in the Discord. Okay, so as it's going from B to A. Oh, okay. No worries, Samuel. So as it's going from B to A, it's on the opposite journey, right? So if we were to catch it as it was going this way, right? Well, then it's not traveling in that direction. Which direction is it traveling in? What do you think? I want to hear your guess. I'm not writing anything. I want to hear your guess. Okay? But think about what direction this is traveling right at that moment, because it hasn't quite gotten up there, right? So at that moment, that arrow is like, Well, I won't even draw the arrow there, right? But what direction is it going, right? So here, the direction that it's going is forward, because that's the direction it goes. This is the path it takes, and then it shows up here, right? And then what direction is it going? Forward, right? Oh, Samuel, you asked me the question. You asked in the Discord, but you're asking me a question again, right? You tell me. I gave you enough information for you to be absolutely sure, right? No questions. Is vector 3 the direction that the box is going, or the thing, right? At that moment, right? Because this is sort of the speed and direction vector at that moment. And what moment is it? It's at P, right? In this example, right? Yeah. Ah, okay, yeah. I think it does. Yeah, there's no drop frames, but I wonder if I can maybe restart, or maybe you can even jump in the Discord. Yeah? Feel free to jump in the Discord and we can talk about it. So I want you to get a little more confident here. I wonder if I can maybe change the settings a bit. Yeah, I think I can. If you also refresh the stream, it might help too for you. So let's just take a look here. What do we got? Can I adjust these? No, I don't think I can adjust these right now. Okay. I mean, I wonder if that helps. Okay, tell me if the latency on that is any better. Okay. I refreshed mine too. So, yeah. Let me know. Okay. So, I'm actually going to close the Discord here, but I'll open it on my phone. Okay, I just saw that message. Maybe like 2 seconds ago there. Same. How was it? Talk to me. How's that delay?